Sorry, Naveen?
Hello.
Naveen?
Yes, ma'am.
Yes. Professor Dutta is unable to unmute himself and start the session. Could you please help him?
Yeah, fine. I'll check.
Thank you.
Okay, I am unable to unmute. Also, Professor Tilman Pfau has joined, and he is also not able to unmute himself and turn on his video. So please see that. Okay, I think we can begin, I guess.
Sure, Professor Dutta, we are waiting.
Okay, so welcome everyone to the online school and discussion meeting on trapped atoms, molecules, and ions. I am Sourav Dutta from the Tata Institute of Fundamental Research, Mumbai. And let me introduce you to our co-organizers, Professor Saikat Ghosh from IIT Kanpur and Professor Bimalendu from IACS Kolkata. So it is not easy for any of us to be a part of an academic meeting in the middle of a raging pandemic. All of us have been affected by the pandemic, some more severely than others. So after a lot of discussions, we still decided to go ahead with this online version of the school. This school was initially planned as a real physical school to be held in the ICTS campus in Bangalore with ample time for discussions. But we were forced to shift to this online version because of the pandemic. This online version will lack in terms of the lively one-on-one discussions, which is a real miss. However, we have a truly outstanding list of speakers working at the very forefront of ultracold trap systems, and we are in for an exciting set of lectures. The primary aim of this school is to learn about the exciting recent developments in experiments with trapped atoms, molecules, and ions, and also to engage with our community of students and researchers. During the last decade, globally, we have witnessed some spectacular developments and striking new experiments in the areas of precision measurements, quantum state control reactions, few body physics, quantum simulation, and quantum computation using trapped atoms, ions, molecules, and Rydberg systems. We are fortunate that many of these frontline scientists will be speaking in this meeting. In India too, several new experimental research groups have emerged, creating a fresh new lot of students and researchers with ambitious plans for exploring new physics. We currently have around 20 experimental research groups in the country working directly with such systems. However, we as a part of this young community have not had ample opportunity to meet each other over extended periods or share our thoughts. And there hasn't been any focused school on experimental AMO physics in the last decade. Furthermore, our AMO community often lacked broad international exposure, and many of us worked largely here in relative isolation. Filling this gap is the precise motivation for arranging this school, to bring together researchers across the globe and the Indian community, forming networks, connections, and most importantly, learning directly from the experimentalists who are transforming the field in spectacularly new ways. The school is also aimed at creating a long-term platform for experimentalists here in India, where ideas and technical know-how can be shared freely among researchers, thereby developing a strong community. Historically, this has been the defining ethos in experimental AMO community, which we strongly feel has been the key to the many remarkable discoveries in this field that has existed only for 3 decades or so. On a different note, the timing of this school is also nearly perfect in the bigger scheme of things. The government of India has recently announced the National Mission on Quantum Technologies and Applications. This initiative is expected to boost experimental efforts in the area of cold trapped AMO systems as well. It has also struck a chord with the young student population of India, who are now interested in exploring modern AMO sciences as a serious career option. With the influx of human resource and funding, there is tremendous hope and enthusiasm to propel Indian experimental AMO programs to global standards. We are excited about the excellent set of lectures in the school. We are very thankful to all the lecturers for agreeing to deliver the set of lectures, and we look forward to their overall guidance as we build towards new cutting-edge experiments in India. We are also very thankful to the ICTS support staff for their help in organizing the meeting. So before I hand over the mic to the Director of ICTS, Professor Rajesh Kumar, for a formal opening remarks, let me remind everyone to please mute their microphones. And you may post your questions in the chat box, which is a preferred option, and then they will be relayed to the session to the speakers by the session chairs. Otherwise, you may also use the raise hand option. So with that, I'll conclude this introduction, and I will hand over the microphone to Professor Rajesh Gopakumar. Professor Gopakumar, please.
Yes, thank you, Sourav, and the other organizers, Saikat and Bimalendu, for putting together this program. As you just mentioned, it's a very difficult time here in India, particularly for everyone, and I'm sure everyone is affected in some way or the other by the ongoing pandemic, and of course people from the other parts of the world as well who have joined in. I'm sure it's not easy for people, but I'm glad the organizers went ahead with the decision to have this online meeting, since for the many students and the members of the community that Sourav just mentioned, it is very, it's good for everyone's morale and to keep up your sort of scientific activity to have these events. And this is why ICTS has been organizing several of these online programs, which were originally supposed to be held in person in campus. We still hope that we can have a version of this program later, provided all the scheduling, rescheduling logistics can be worked out. And as you know, the time scale on which we are talking about is very uncertain. We were cautiously optimistic that we might be able to start programs towards the latter part of this year in person on campus, but now that seems very unlikely. In any case, these online meetings certainly have the advantage that a lot of people can join in, and I see there are at least 115 participants on this call. Usually in our physical programs, due to the limitations of space on campus and lecture rooms, etc., smaller number of people are able to participate. So it's a trade-off, and I guess one looks at the positive side of things, even though one misses the liveliness of the in-person interactions. So in any case, I hope the younger participants especially will use the opportunity, all the facilities of the chat and other ways of asking questions to interact with the speakers and try to get the most out of the workshop. Many times I think organizers have had some special tutorial or discussion sessions where the lecturers have helped to clarify some of the details of their talks. So perhaps there will be something like that in this meeting as well. In any case, the younger ICTS programs are aimed at creating a community of researchers, and in the AMO community, as we just heard, which is growing, and it's important that we be able to give an international exposure to the younger researchers, students, and postdocs who are in the community, so that there are collaborations built up between India and the rest rest of the world, and younger people are able to get an idea of the cutting edge topics and work on them. So ICTS, that's been the sort of philosophy behind the ICTS programs. We've had an ICTS as a unique institution in the Indian scientific ecosystem, which does this. It is a part of the Tata Institute of Fundamental Research, which is of course, the original campus in Mumbai, but now we have centers of TIFR across the country. In Bangalore, there are 3 centers, and Hyderabad, Pune, etc. So TIFR is a more pan-Indian institution now, and each center has its own mandate, a special mandate. And at ICTS, apart from our programs, we also have our own in-house research as well as outreach activities. And you can see that we have in this 10 or so years of our programs, more than 10 now, 10, 12 years of programs, we have had a number of topics covered across the sciences. So despite the T in the ICTS, which is for theoretical sciences, we do welcome in our programs experimental areas and places where experiments and theorists can very fruitfully interact. Of course, we ourselves are limited in our institution to having large-scale experimental facilities, but we do have some small tabletop labs in various areas of fluid dynamics, soft matter, etc. So the ICTS programs are all archived, and you will find the lectures even of this program and all previous programs. You'll find them on our YouTube channel, ICTS Talks. And especially for the younger people who, if you want to browse through our set of videos, I'm sure you'll find a lot of interesting scientific content there. And especially in a time of lockdown, I think this is a very fruitful way to spend your time and get acquainted with some of the exciting areas of modern physics or science more broadly. So I want to thank all the lecturers who have very kindly agreed to give talks online, give series of lectures online for the school part of this meeting, and then the speakers of the workshop. So I hope everyone will have a very productive scientific interaction, and as I said earlier, for the students themselves, please don't hesitate to sort of interact very intensively with the lecturers. And my best wishes to the organizers for a very successful school. Thank you very much.
Thank you very much, Professor Gopakumar, for your opening remarks. Now let me introduce the chairperson of the first session, Professor Bhanu Pratap Das from Tokyo Institute of Technology, Tokyo. Professor Das works in the areas of atomic and molecular physics. Since 2015, he has been at the Tokyo Institute of Technology. Before moving to Tokyo, he served as the director of the Institute of Astrophysics, Bangalore. So with this brief introduction, may I invite Professor Das to take over as the chairperson of this session. Thank you.
Okay, okay, thank you very much, Professor Deb. Can you all hear me?
Yes, sir, we can.
Okay, thank you. Yeah, all right, okay. So, so it's my pleasure actually to introduce the first speaker of the session. That is actually the first lecturer, I should say, of the school, Professor Tilman Pfau. He's a professor and chair of photonics at the University of Stuttgart in Germany. And he's also the head of the 5th Institute of Physics at the University of Stuttgart. Professor Pfau is undoubtedly one of the leading experimentalists in the field of ultra-cold atoms, and has made many, many profound contributions to this area. I think he's probably best known for his work on dipolar Bose gases. In particular, I think his group made the first observation of Bose-Einstein condensation in chromium, which is a dipolar atom. And they did a series of very pioneering experiments in this field, which led to quantum droplets. I think that was probably about 5 or 6 years ago. And then more recently to dipolar supersolids. The supersolid phase, I think that's the subject of his lecture. That's it's a phase that had defied observation, experimental observation for a long time, but with cold atoms, it has been observed. And so, I think all of us look forward to his lecture on supersolids. And because of his outstanding work in this field of ultra-cold atoms, he's won numerous prizes and the fellowship of a number of societies. I mean, they're too large to be mentioned. I guess they're too numerous to be mentioned. So I'll just mention a few. He's the recipient of the Herbert P. Broider Prize of the American Physical Society, which is for outstanding work on experimental atomic and molecular physics. He's also the recipient of the Gentner-Kassler Prize of the French Physical Society and the German Physical Society. And he's also an elected fellow of the American Physical Society and the American Association for the Advancement of Sciences. So with these few words, I would like to invite Professor Pfau to give his first lecture. Professor Pfau, please.
Thank you very much for these kind words. Can you hear me?
Yes.
Yes.
Okay.
Yes.
Let me just share my slides. Here we go. So again, thank you very much for that kind introduction and the possibility to speak here, to give a lecture. I will actually give 2 lectures during that week. I decided to split it into 2 quite different topics. The one that you mentioned on supersolids, the dipolar gases, and so on, I will give on Wednesday. And today I will speak about another field where we are active, and that is Rydberg atoms and molecules. So today I'm going to introduce that field to you. And as this is a school, please consider this to be a lecture that is introductory in character, and it contains a few recent results, but the main intention is to familiarize you also, mostly hopefully the young people in the audience, with Rydberg atoms. And in particular, I will focus on their interactions, the strong interactions that make them so interesting for all kinds of applications, from quantum computing to quantum simulation to quantum optics with single photons, but also to chemistry. New kinds of chemical bonds have been discovered, and even charge transport measurements through quantum gases and so on, as you will see during that presentation. So let me start by showing the picture of Johannes Rydberg, who was a professor in Sweden at Lund University, and he is sort of most famous for his Rydberg formula that you're all familiar with, describing the excitation spectrum in the hydrogen atom. And there's, of course, the Rydberg constant in front of this famous formula here. And of course, at the time, that was pioneering work, that led to the quantum mechanics in the way we know it today. Now, of course, Rydberg atoms are a very hot research topic even today. There are a lot of pioneers in that field. I'm just mentioning Tom Gallagher here because he has written a very important textbook. So if you want to read more about Rydberg atoms, mostly about the single atom aspects, about the Rydberg spectra and the various shifts and the spectral properties of Rydberg atoms, I can highly recommend this book by Tom Gallagher, one of the pioneers of Rydberg spectroscopy, also with cold atoms. But I also can mention, of course, many other pioneers like Pierre Pillet, for example, that have shaped this field in the very early days of cold atoms, laser-cooled atoms, as they came up. So Johannes Rydberg was working at Lund University in Sweden. Here you see actually a building. This was where he had his lab on the campus in Lund. I have this picture because I had the pleasure to give a lecture there in that building in 2016. And you find the picture of Rydberg everywhere on paintings and pictures on the wall. So it was a great honor for me to speak in Lund at the place where all the Rydberg physics in a way has started. Now, coming to our activity, this is the campus where I'm from. That's in Germany, Stuttgart University. We have a campus outside the inner city. You see these two big buildings here, and where the arrow points here on the 4th floor, on the right side of that building, is where we are doing our Rydberg experiments and this is also the building that you see in my Zoom background right behind me. So I wish I would be able to travel to see you guys in person, because my experience still is, that the lively discussion that you have with people in person is so much more intense than what you can do in a Zoom meeting like this. But I would like to ask you to interrupt me anytime if you have questions or comments. I will try to also make breaks in between and ask you for questions whenever you might have them. In this lab, I'm working with a great team of people, and I'm mentioning right in the beginning because afterwards I might maybe forget about this. This is our team, and we have a lot of activities, as you have heard. We are working on dipolar gases. We are working on Rydberg atoms. And actually, most recently, we also started the quantum computing activity using Rydberg atoms. And so if you are interested to join this team, we are hiring PhD students and postdocs at this moment. As like in India, there is a large push for the field by an investment by the federal government, in particular in quantum technology, also using Rydberg atoms in particular for quantum computing. And we are sort of building the first German Rydberg quantum computer in Stuttgart based on this kind of funding. So what is the topic of my lecture? It's a lecture, as I said, and I thought I try to introduce the interesting things about Rydberg atoms, and these are the interactions that they actually have, because they are extremely strong, as you will see. The Rydberg interaction is where I want to start with, because that's the physics of the so-called Rydberg blockade, or the physics behind that Rydberg blockade that makes this a strongly interacting quantum many-body system, if you like. But I mean, I thought I introduced this kind of interaction to you in the first part of that talk. In the second part, I will then move on and discuss the interaction of a Rydberg atom with a single ion. And this ion is producing, of course, an electric field. And as we will see, these Rydberg atoms are very polarizable, very susceptible to electric fields, and therefore there's not only a Rydberg blockade, but also there is an ion blockade, so that the Rydberg excitation can be completely blocked if there is a single ion around. And I will describe that kind of interaction that is even stronger than the Rydberg-Rydberg interaction in the second part. And at the end, I will then also report on the interactions of Rydberg atoms with ground state atoms that you might have around in a dense sample, like a Bose-Einstein condensate, or even in a vapor cell. Yes, you will have a background gas, let's say a buffer gas, or just unexcited atoms. This green guy is one of them, ground state atom. And then we will learn that this electron, this Rydberg electron, actually has a strong interaction with this ground state atom, and that gives rise to new binding mechanisms, the so-called ultra-long range Rydberg molecules. And so if I have time at the end, I will describe those to you. By the way, if there is someone keeping the time, please give me warnings if I'm going over time at the end. So to introduce Rydberg atoms, we are going to first discuss single atom properties before we go to the interactions, just to get you familiar with the typical scaling laws that we have in Rydberg atoms. The first thing is the size. The size of a Rydberg atom is huge compared to everything else we have in the atomic world. And it scales with the so-called principal quantum number, which counts the numbers of excitations to the square. And just to give you an example, here we have a 43 S state, which is an n equals 43 state. It is already on the order of 160 nanometers, basically in radius. That's 3,000 times larger than a normal atom would be. This A0 is a Bohr radius, the typical length scale. Yeah. And in contrast to what you would think of an excited atom, naively, the lifetime of those atoms is relatively long, and it actually increases with the third power of this principal quantum number. So this lifetime gets longer and longer the higher you excite it. And the typical lifetime of that 43, just as an example state, is on the order of 100 microseconds. That gives you ample time to do experiments, yes, that can happen, let's say, on the 100 nanosecond time scale. Yes. In addition, they are very susceptible to electric fields, and that is expressed by the polarizability. That polarizability is usually negligible for ground state atoms. I mean, lab electric fields are usually, static ones at least, are not strong enough to polarize them such that you get a sizable Stark effect. But in the Rydberg state, as we will see, this polarizability scales like the 7th power of the principal quantum number. And if you go now from a ground state to a, let's say, 43S state, you can see that with 1 volt over 1 centimeter, you can shift the Rydberg line already by 10 or 20 megahertz, which is, of course, something that you can easily observe and use. Okay. So if we talk about the radius of Rydberg atoms, really what we are talking about is, of course, the wave functions. And here I'm plotting what you all know, I hope, the basics, basically, of the hydrogen wave function. If you are increasing the principal quantum number in that first entry here of that triple of the quantum numbers n, l, and m, then you see that the outer turning point of the electron, in this case of an S state, yeah, the L is 0 here, moves out with this power law n squared. Okay. And if you go on with that and you go to very large principal quantum numbers like n equals 100 or even 200, which is what we can access in our labs, really. I mean, we do experiments up to n equals 200 in our lab. Then you see that this radius goes all the way up to 4 micrometers. Yes, that's a huge object. It can be even larger than for example, a Bose-Einstein condensate itself, which means that you can prepare a situation where the Rydberg electron spends most of its time outside the condensate while the ionic core sits inside that condensate. Okay, so the rule of thumb for you to remember is the n² law. And if you have n equals 100, that's the red curve here, you see that the radius is about 1 micrometer for an S state. Yes. So that's the rule of thumb. Yes. If someone asks you what is the size of a Rydberg atom, you should answer 1 micrometer for n equals 100. And from there on, you can just use the n² scaling. Okay. This is just to compare to other things. Of course, these days, viruses are important, of course, and you can see that 4 micrometers here, brings you in the range that is much larger than those viruses. It's actually even larger than some bacteria that we have. Yeah. Now let's talk about the lifetime. Again, we are looking at our example state 43S here. What can such an excited Rydberg atom do in order to decay? Well, one thing is it can undergo spontaneous emission back to the ground state. And here you see the transition rate to different manifolds, basically, of the excitation spectrum. And the largest probability to come from 43 back to the ground state is shown by that bar here with a transition rate of about 5,000 per second. So that is spontaneous emission of that huge Rydberg atom down to the tiny orbital in the ground state. And as this overlap integral is so small, this is actually not a very big rate here. Yes. However, there are other states. You can go to the n equals, in the rubidium case, to the n equals 6, 7, 8, 9, 10, and so on. And if you care about the total lifetime due to the spontaneous emission back to any of those states, you have to integrate over those blue bars here. Yes. And there, if you do that, you end up for the 43S state with a spontaneous lifetime of about 100 microseconds. However, there is a second process that is possible for Rydberg atoms, at least if there is a finite temperature in the environment, and that is to get excited or de-excited by a stimulated process that is stimulated by blackbody radiation. Yes. Because the neighboring states are only separated in a frequency range between 100 gigahertz and a few terahertz typically. That's exactly where the blackbody radiation already provides thermal photons. And therefore, if you start in the 43S state here, you can get excited to even higher principal quantum numbers by the absorption of those thermal photons, or you can get stimulated by these blackbody photons to lower lying states. And these are the red bars here that you find in that histogram. And if you are integrating these decay options that basically take your initial state 43S to some other state, then you end up with a similar lifetime limitation due to blackbody induced depopulation. And if you take those two things together, then you see that this 43S state will live in a normal thermal environment at room temperature for about 50 microseconds. Okay, so it's always important to keep in mind that at least in the normal cold atom experiment that is not using a cryogenic environment, as some people do, but it's a lot of more effort, then the lifetime of Rydberg atoms, grow with the principal quantum number, and there's a difference that depends on the presence or absence of blackbody radiation as shown here. And you see that if you go to n equals 80, for example, with blackbody radiation, you can reach a lifetime of about 200 microseconds. It depends a little bit on whether it's an S state or a P state, but that's the order of magnitude. All right. So that gives us ample time to do interesting experiments. Yes, hundreds of microseconds. Yes. There's another important thing that we need to understand about Rydberg atoms, and that is the concept of the quantum defect. if you compare the excitation spectrum of a hydrogen atom here on the right side with the excitation spectrum of an alkali atom, and rubidium is just one example here, then you see that the excitations are actually shifted with respect to hydrogen. And that shift can be grasped by a so-called quantum defect, which is well known for the alkalis, and you find the numbers for the different L's here. And what does this number tell you? Well, it tells you that the real core of the rubidium atom is not a singly charged proton as in the hydrogen case. It is a singly charged inner shell that is shielded by the inner electrons. But the ground state is the n=5 state. So that means there are 4 fully filled shells inside already. And if you have an S state on the left side here, then your electron will eventually dive into that charged cloud and experience more charge than just a single charge if it has some probability to come near to the nucleus. And therefore, the n=5 ground state here, for example, is already shifted with respect to the hydrogen n=5 state by a substantial amount. And this is exactly expressed by this quantum defect delta that depends on the orbital angular momentum L here. Yes. So it describes effectively the shielding of certain orbitals by the inner shell electrons. Yes. But you see, these are not integer numbers. So that means now that while in hydrogen, there is a large degeneracy of any excited state. All the L states are more or less degenerate here in hydrogen. This degeneracy with respect to L is lifted due to the different quantum defects of the different L states. Okay, that's going to be important later on. So experimentally, how do we reach the Rydberg states? Well, I mean, if you go through it in rubidium, for example, then you see, okay, you can do it, for example, with a 2-photon excitation by a red laser and a blue laser, for example. You can absorb 1 photon here to get to the P state, the n=5 P state, and then go to any of those Rydberg states, high-lying Rydberg states up here in the S manifold, or due to selection rules, also to the L=2 if you do 2-photon excitation. You can also go directly from that state to the Rydberg state, but then due to selection rules, you are forced to end up in the P manifold here, in the L=1 P manifold. And that laser is actually below 300 nanometers in wavelengths. That's possible, but it also comes with some problems, of course. Yes. So most of the experiments use that 2-photon route. There are actually alternative routes. You can also go from that n=5 to the n=6 state here first with a blue laser, and then with an infrared laser to the to the NS or ND states here. These are all alternatives that you have depending on what are your specific needs. In a nutshell, you buy some of these lasers. And what is important is that this final transition here has a very small dipole moment, a very small transition matrix element, and therefore you typically need a lot of power to drive this one here. Yes. Okay, so if we now put these Rydberg atoms into an electric field, then we are all familiar with the Stark effect that is going to shift the energy levels according to the Stark effect. And probably you have seen that in hydrogen. In hydrogen, due to the large L degeneracy here in the N manifolds, the Stark effect is a linear one. Yes, I mean the orbitals are all degenerate, and therefore if you apply an electric field, the new eigenstates will already have a dipole moment that can be shifted with this electric field in a linear fashion. Okay, Now it becomes important if you go to alkali atoms that this is not the full picture, because we do have that quantum defect. And the quantum defect means that, you know, the 43S state that we have looked at before is actually not a degenerate state. It is a single non-degenerate state here that is due to that strange number of the quantum defect, basically quite lonely here in the spectrum. And we are going to excite with our two-photon excitation either S states or P states. And for the P states, the same is true. They are not degenerate with the hydrogen manifold. And therefore, those two states actually have a quadratic Stark effect that grows with the square of the electric field, because the electric field will first have to induce a dipole moment, and then that dipole moment can give rise to a shift. Okay. So that's important. And the polarizability of that state here now comes with it n to the 7 scaling with the principal quantum number. Now, such a Stark mat can be easily experimentally measured. That's some unpublished data here, where you see we just have a little cell, a glass cell that we fill with rubidium vapor. And we just measure, in this case, actually the current across those two electrodes as a function of the frequency of our laser, which is plotted here, and the electric field that we are applying across those two plates. And you can see that there's a quadratic effect, at least for small fields. And then at higher fields, something interesting happens. What is this? Well, if you go back, you can see that at higher fields up in this region here, the hydrogen-like states are coming down in the spectrum, and they are crossing that line here. And these crosses basically are actually avoided crossings that you can see here, and that lead to a little bit of mixing of these states together, and you get these crossing points here in this experiment quite nicely visible. Yes. So this is just to show you, you know, it's very easy to measure the Stark effect in Rydberg atoms. And that's actually what we need to do in order to do experiments with Rydberg atoms. Here you see our first chamber where we produced Bose-Einstein condensates 15 years ago, which also led to the first Rydberg excitations in Bose-Einstein condensates. And what you see is that in addition to a normal steel chamber, we had to put electric field plates inside to control the electric field. Because even though this is steel here, you always have some windows nearby where there are charges and so on that give rise to little small electric fields that you want to compensate. So one way to determine the electric field here in the center of your vacuum chamber is to measure the Stark shift. Yes, and here on the right side, you can see a Stark shift measurement as a function of electric field. And note that this time we are talking about millivolts per centimeter. You know, the dimensions are centimeters here. So you will have to control the voltages on the millivolt level to zero out the electric field. And you will have to do that in all 3 dimensions. Okay. So if you can do that, then you can excite, for example, very high Rydberg states like 202S state is this final measurement here. And you see that this state has a shift. If you apply a few millivolts, 2-3 millivolts of a few megahertz here already. Yes. So that is actually something that needs to be controlled in your experiments if you want to do successful experiments with high-lying Rydberg. Rydberg states. Okay, what's the record? How high can you go? I mean, what's the experimental limit? Well, this is an experiment that was done at Rice University in Barry Dunning's group some years back. Here you can see that they have reached principal quantum numbers all the way up to 400 or above. Yes, and you can actually see the reviving frequency because that's the distance between those Kepler or between those states according to the correspondence principle. So there's a question now, as I can see. So please go ahead. At least there's a raised hand. Do you want to unmute yourself? Yeah. I cannot hear you yet. So,
well, there's a question in chat, but
okay. Can you? I didn't follow the chat. So, what is?
Yeah, it's not very clear to me. It says you mentioned characteristics of Rydberg atom, polarization, principal quantum number, wave function. But why only Rydberg atoms?
Well, that's the topic of this talk.
Yeah,
I would have said.
Yes.
Rydberg atoms, the name is basically referring to all highly excited atoms. Doesn't matter whether it's rubidium, strontium, hydrogen, you name it. Even molecules have Rydberg states even. So what I'm telling now is the general features of all these very highly excited states. And it depends on your taste, what you call a highly excited state. I would say everything above 20 or so, I would say, is a Rydberg state. Yes. Okay.
I think that's all. So perhaps you can proceed with your lecture.
Yeah. Okay. Thank you.
Thank you.
So please remind me. I'm not following the chat. So if someone can follow the chat, then please tell me that if there are questions.
Okay. Sure. I'll do that.
Okay. So here you can see that if you oops, now I can. Okay. If you take the difference between those two states, yeah, that's En minus En minus 1, sort of that's the distance between neighboring Rydberg states, then this corresponds to the Kepler time, the orbit time of an electron around the nucleus. And in this case, that corresponds to about 4 nanoseconds. That's something that you can experimentally even resolve. Yes, you can see the electron moving around that core, basically. Okay, so that's the world record, I would say, by Barry Dunning's group in Texas at Rice University in strontium atoms. Why didn't we reach that? I mean, we reach only up to 200. Well, the reason is we are doing this in a very much smaller box here. They are doing this on an atomic beam experiment. I've seen it once. It has tens of centimeters dimensions. And the name of the game is, again, the control of the electric field, the residual electric field, which in their case is much better possible because they have a huge box. In our case, that box here has centimeter size only because it also has a Bose-Einstein condensate actually inside and some optics nearby to do a high resolution imaging. And that limits our electric field control to a fraction of a millivolt per centimeter. And therefore, in our experiments with Bose-Einstein condensates, we are limited to a principal quantum number of about 200. I mean, okay. So let's summarize that single atom Rydberg part and ask for questions at this point, if there are any. I mean, this was just to set the stage for non-interacting Rydberg atoms that we know what we're talking about. Are there any questions at this point?
I think there's one question. Do AC Stark shifts from the exciting lasers matter?
Yes, they do, but they are not much larger than the usual ones. Actually, yes. You can consider this electron here of the Rydberg atom. Let me just. Oops, my pointer is sort of frozen here. I cannot move it anymore. Sorry, my computer is sort of having a problem right now. Okay, now here we are. This electron here basically can be considered as a free electron almost, and if you shine a laser on that electron, it undergoes a so-called ponderomotive motion, and that gives rise to an additional shift. That has been investigated, and that has to be added if you are working in a laser field. Yes. So what I was describing was just DC Stark effect, and the question is a very good one. there are also AC Stark effects in a laser field.
Yeah. There's one more question, or maybe two more actually. So what is the experimental procedure to measure the Kepler time?
Oh, here in this experiment by Barry Dunning, it was not measured directly. They just measure the excitation spectrum here, and they see this distance. And what I told you is then I inferred sort of the Kepler frequency from that distance here only. Yes, but if I'm not mistaken, they have also done direct observation. And what you need to do then is you need to prepare a wave packet that is really spinning around. But yeah, I would have to go back to the paper to tell you exactly how they did it. But I think they also observed the spinning electron wave packet around the nucleus. Yeah.
Okay, so we can take just one more question before you proceed. The question is, what are the significant differences between Rydberg states in an atom versus in a BEC, pros and cons?
The Rydberg state is always an atomic state. And the question is, what does the BEC do to that Rydberg electron? When
yes, I think so, yes.
And there will be shifts, like pressure shifts that you know from normal spectroscopy as well. And that is the final part of my talk today. There will be interactions that give rise to actually bound states of atoms that are sitting inside the Rydberg orbit. Yes.
Okay, I guess you can proceed, I think.
Okay, I'm just proceeding. I already see that we will be running out of time in the end. So let's see how far we go. Rydberg interaction. I mean, that's why many people are interested in this field these days. And the reason can be summarized in this plot. Here's the interaction strength. Here's the interatomic distance. That's the logarithmic, doubly logarithmic plot. So if you think about the interaction between two ground state atoms, by van der Waals interaction, it has a 1/R6 potential. Then you see, of course, this is a very weak interaction on that scale that we are talking here. Yes, 100 nanometers, 1 micrometer, 10 micrometers. It's expressed in hertz, so it's less than 1 hertz, so it's totally negligible at this kind of scale. Yes, there's a little bit larger interaction between magnetic atoms, magnetic dipoles. At the 1 micrometer, it's still below 1 hertz, so it's nothing that you should have considered in your experiment. Yes. If you consider now the interaction between excited atoms, let's say one excited atom and the ground state atom, then the dipole moment gets as large as typically 1 dBi or so. And then it can already be sizable. Typically, as you know, the interaction is on the order of the line width of the transition if you go to a distance lambda over 2 pi. Yes, that's this blue line here. Yes, but the interaction between two Rydberg atoms is orders of magnitude larger than that. That's here shown for 35S, which is actually a low-lying Rydberg state. If you increase the principal quantum number, you can easily move all the way up here. And the task of this part of the talk now is to understand that behavior, starting from a 1/R3, falling over to a 1/R6 van der Waals interaction. What's going on here? Yes, why is it so strong? And what is the nature of that interaction? Does it seem to be first dipole-dipole at short distances, and at long distances, it's a van der Waals interaction? If we have such a strong interaction, you know, that's what you see here in this plot that I actually took from that reference. I can only highly recommend that for everybody who wants to enter the field, by Mark Safman, Thad Walker, and Klaus Möllmer. If you have such a strong interaction that is long range, it is clearly also tunable, as we will see. It is switchable. So if you just excite the atom or de-excite it, you can switch this interaction on and off. You can switch it in a conditional way, depending on the state of a qubit, for example. And therefore, it is very important to implement two body gates in quantum computation, yes, and in quantum simulation, yes. It is also responsible for the high optical nonlinearity on the single photon level, as you will probably learn in the lecture by Vladan Vuletic that is also teaching here in that school, yes. So this interaction is very strong and very interesting. So where does it come from? Well, let's go back to the simple physics of a two-level atom first, yes. So here I show you something that is a little movie that shows you as an S state, that's the left one here, and a P state atom that is excited on the right side. And if you put one in the excited state and one in the ground state, and one is on the left side, one is on the right side, then this is not an eigenstate of the system, yes? The system will constantly exchange interaction from left to right. And the way it does it is it takes these initial orbitals that are round and P shaped, basically dumbbell shaped, like now, and induce a dipole moment by their mutual interaction. And that's basically a resonant electric dipole-dipole interaction between those two atoms here that you can see directly if you just observe the charge distribution of that orbitals, of these orbitals that are evolving in time. Essentially what you see here, if there's a superposition between the lower and the excited state, is a superposition between S and P, and therefore the charge has the maximum, allows for the maximum dipole moment on both sides, okay? So then there is a dipole-dipole interaction between those two-level atoms that falls off like 1 over r to the third power. By the way, this process is very well known since many years, and it was discovered or first discussed by Theodor Förster, who actually was a university professor in Stuttgart in the chemistry department. You see the chemistry department right behind me in that building on the left side. And it is this process that I'm showing you here is called Förster energy transfer. And it appears between atoms that are sharing one excitation. Okay. Now, if you have Rydberg atoms, the picture is actually quite similar, yes, than that simple Förster energy transfer. The situation, however, is slightly different, as this initial state, the S state here, can be surrounded by an excited state. It's an even higher excited Rydberg state, but there can also be a lower state, let's call it the P state, at some lower energy, okay? So if I now take those bare states here, and I take two atoms, then what I really have is a pair state basis that consists of these two S atoms and a PP prime state that contains one excitation above that S state, P prime, and one state that is actually at lower energy. Now, if those two distances here are equidistant, then this delta here, so-called Förster defect, is 0. And this PP prime state and the SS state are degenerate. Of course, there are also the other states, SP and SP prime, but they are far away in energy. And usually this delta here is small enough such that we can consider this to be our new two-level problem. Yes, let's consider that two-level problem here with that little delta in here. If we write the Hamiltonian for that, then we see that this delta appears here on the diagonal. And on the off diagonal, we see this dipole-dipole interaction between the dipole moment that goes up, S to P prime, and the dipole moment that goes down, S to P. That's D1 and D2 here, and it falls off like 1 over the distance between the two particles with the third power. Now, such a 2x2 matrix can easily be solved, yes, for its eigenvalues. You see these eigenvalues here with the delta included and also that off-diagonal term. And for example, now, if this delta is larger than the D1, than this off-diagonal term, then you can Taylor expand that square root here, and you end up with a energy shift, an eigenenergy basically, that goes like the square of that dipole-dipole interaction, explaining the 1 over R6 behavior. And and a front and a factor in front that goes like -1 over the detuning delta here. Yes. So this ends up in a van der Waals interaction that is described by a coefficient C6 that contains the two dipole moments, d1, d2 to the square, and the delta here. And note that the sign of that C6 coefficient now depends on the detuning here. Yes. On the other hand, if the delta is very small now, or the distance between the atoms is very small compared to that quantity, then you can essentially neglect that little delta in here. You can take the square root directly, and you end up with a dipole-dipole interaction. Okay. So actually now this delta depends on the details of your spectrum here, and that depends on the quantum defects as we have explained. And therefore, whether this excited state here is closer or farther away than the lower state really depends on all these issues about the quantum defects. So the sign of that C6 coefficient can be, in some cases, repulsive, in some cases, attractive. And you should remember, of course, that the van der Waals interaction between two ground state atoms usually is only attractive. And the reason for that is there is no lower p state here. There can only be positive deltas. But for Rydberg atoms, that doesn't have to be the case. It can be repulsive or attractive. Okay. Now, if you tune that delta to 0, then you end up with a Förster resonance. Okay, so that means that this dipole-dipole interaction is dipolar all the way to large distances. And of course, the interaction strength is enhanced. Okay, now the question is, can we tune that delta to 0? And the answer is yes, these are the so-called Förster resonances. And the way to tune it is to use electric fields, because we have Stark effects that can shift around the energy levels. Okay, and we can make that delta go away. So here you see a real example now of how the orbitals look like in a particular Förster resonance that I'm going to show you. So you see that it looks a little bit more complicated than the original Förster resonance, but you can again see that you start with some initial state that has a funny orbital, yes, with this little donut shape here, yes. But then as far as the time goes by, this left one gets de-excited, the right one gets excited, the orbitals change a little bit, the dipole moments develop, and then this process starts to oscillate. Okay, so this kind of mechanism is what gives rise to a real Förster resonance. Here I show you this example. There are many Förster resonances, but that's one that we investigated many years ago, starting from the 44D5 half state, which has neighboring states which are dipole-allowed transitions to a P and an F state that are oscillating at almost exactly the same frequency around 60 gigahertz. Yes. So if you calculate the Förster defect for such a situation, then the pair state 44D plus 44D and the 42F 46P are only separated by 60 megahertz. Okay. So if we now tune that by an electric field, you can see that the pair state is this blue line here, and these other pair states can cross that other pair state at certain positions. And without going into the detail, we could measure that by just looking at some Ramsey sequence that shows you nice interference patterns shown down here. And if you analyze those interference patterns, then you can see at certain electric fields, these three resonances here, these electric field resonances that actually show you that around such a resonance, we can switch from attractive van der Waals to repulsive van der Waals, and directly on resonance, we do have a purely dipolar interaction. I don't go into the detail of this experiment, but I hope you have understood now what is the nature of the Rydberg-Rydberg interaction. So if you now have, let's say in this example, a very strong repulsive van der Waals interaction, as shown here, yes, then if you again look at pair states as a function of the distance, and you look at the two ground state atoms, then there's essentially no interaction, and that is a flat line. There's also no interaction almost between the ground state atom and the Rydberg atom, which is the excited atom E here. So that's a flat line. But between the two excited Rydberg atoms, there is, in this example, a very strong van der Waals interaction that is repulsive. So now if you excite your atom with a laser that has a certain line width, gamma, or if it has a lot of power, you power broaden that line, then this broadening here defines a length scale, which we call the blockade radius, below which it is not possible, because the lasers are no longer resonant with that interacting pair, to excite that second atom, okay? So that's called the Rydberg blockade, okay? Now, if you think about an ensemble of atoms like this, you excite the atoms by that laser that wants to excite them, then this length scale actually means that the Rydberg atoms have to keep the distance. They have to keep the distance of that blockade radius. You cannot excite another Rydberg atom if there is already one atom. So that's shown here by that little graph. And if you put the numbers, then this Rydberg blockade radius is on the order of 10 micrometers, which is large. And you find in a Bose-Einstein condensate thousands of atoms inside such a blockade volume. Okay. So you can try to isolate one such volume. Yes, you produce a volume that only has a few micrometers, and then ask yourself, what's the quantum mechanical state of the excited ensemble here? Because if you have such an ensemble, you have thousands of atoms, you excite it, you don't really know which one was excited, right? So quantum mechanically, you have to write down a superposition of, let's say, the first atom that you have in your ensemble is excited and all the rest is in the ground state. Or the second one is excited and everybody else is in the ground state. Or, and then there are n terms, if you have n atoms, or the last one is excited, okay? So there is a one superposition state, you can call it a W state, with this norm here in front, 1 over square root of n, that describes that whole object here, which contains one single excitation. Now, the ground state of that is trivial, yeah? It's just a product state, yes? Everybody is in the ground state. So if you drive a transition now to excite that guy here, then as you have n possibilities to excite it, the overall Rabi frequency of exciting that atom is enhanced compared to the single atom Rabi frequency by a factor of square root of n. So in that sense, this thing here acts as a two-level atom, although it contains thousands of atoms. It's sort of a collective two-level problem. And that's why we sometimes call this guy a superatom. Yes. Essentially, these are the two important levels that are coupled by our light field. Yes. And these ideas about these collective states go all the way back to paper that I cite here, that is 20 years old. So this idea can be tested. That was done in the pioneering experiments by Antoine Brevet, for example, also more than 10 years ago. If you put one atom in your box, then you see the red Rabi oscillation. If you put two atoms in the box, then you see that the Rabi oscillation actually speeds up by this factor of square root of 2. And well, that's what is shown here on the right side. That square root of 2 is exactly the speed up that they have measured. In another paper a little bit earlier even, we have measured that for n equals 1000, and we could measure that n equals 1000 speed up. And there are even more papers, of course, by now that have demonstrated this. Now, what is it useful for? There are many possible applications, of course. One of them, again, is by Alex Kuzmich here, where he has trapped a lot of atoms, ultra-cold atoms, in a dipole trap that was smaller than the blockade radius. And he excited these atoms to the Rydberg state and brought this excitation back to the ground state in a 4-wave mixing experiment, such that this final photon that is shown here actually transfers that W state that you have produced in that Rydberg state back into the light field. And as there is only a single excitation due to the Rydberg blockade, it will produce a nice single photon source on demand, actually. Yes. And here you see the proof. That's the measurement of the G2 correlation function at 0 delay as a function of the principal quantum number. You see that at low principal quantum number, there's no blockade. The G2 is just what you expect from a laser, 1. And then it goes down all the way to almost 0 if the blockade at n equals 100 is very large. Okay, there are many other experiments, of course, and I think you will hear also from Vladan about these kind of experiments. What I want to show you here is that this blockade effect is so strong that it doesn't require even cold atoms. It can even work at room temperature in a thermal vapor cell. Okay, so that means you have to build a glass cell that contains these atoms here, and you have to do 4-wave mixing to the Rydberg state, just like in this Kuzmich paper. And that will lead to a single photon source where the single photon comes out on demand in a direction that is given by the phase matching of the 3 other laser fields. Okay, so the experiment was done like this. We used a wedge cell, glass cell. Actually, you can see a picture of that glass cell here. You can also see Harald and Robert making glass cells here with a flame. Yeah, that's actually nice experimental physics. And you can see that this glass cell here shows some Newton rings. So it has a distance between 2 glass plates that is on the order of the optical wavelength, so smaller than 1 micrometer even. And that is smaller than the blockade radius. And therefore, if you focus a laser beam into that wedge cell, you can isolate a single superatom, as we call it, inside that wedge cell here. Yes. So that's the experimental setup. Yeah, it's pretty simple. You just put this glass cell between 2 focusing lenses here, and you do your 4-wave mixing. Actually, we did this experiment with rubidium, and here you see at the 32S state how the interaction potential actually really looks like. It has a nice van der Waals repulsive interaction all the way up to 5 gigahertz. Yeah. That's important because in a vapor cell you have a large bandwidth, and the blockade will only work if this potential is clean all the way up to the bandwidth of your experiment. For example, if you would do the same experiment with cesium, you could already tell it will not work. Yes, the blockade is not perfect here. Yes, and that has to do again with the quantum defects that in cesium are just almost integer for the S state at least. Okay. So now you can do that 4-wave mixing. I don't go to the detail of that experiment. Everything is on the nanosecond time scale, as you can see here. And we can produce that G2 measurement again and show that, yes, we do get a G2 that is clearly below 0.5. That's sort of the limit that you have to reach in order to demonstrate that you have actually made a single photon source based on the Rydberg blockade. Okay, so here you see that we can measure that G2 also as a function of the cell length. So we just measure it at different positions in that cell that is wedge shaped. So we can increase that cell length from, let's say, 0.5 micrometer to 1 micrometer. And then you see that the blockade actually goes away and that single photon source doesn't work anymore. Okay. So that basically concludes my part on the Rydberg-Rydberg interaction. I hope I showed you that these are really strong interactions. Yes, even in thermal vapor, like at ambient temperatures, you can use that strong Rydberg-Rydberg interaction to produce a quantum many-body state like this W state, and you can read it out in order to generate a single photon. Yes. And of course, if you do it with cold atoms, it works even better. And that's where you, of course, then for quantum computation and so on, want to get also the extremely high fidelities that you need in order to compete with other platforms. Are there questions up to this point about the Rydberg interaction?
Well, I don't see any questions on the Rydberg interaction. Oh, no, I think there is one.
Okay.
Okay. Why are the lasers that are used in the 4-wave mixing experiment in the nanosecond scale?
Yeah, that's a very good question. Let's go back to that. Here you see the nanosecond time scale, and here you see the 3 laser pulses that we had to apply. The reason is that in a thermal vapor, if you are working with different wavelengths, you have Doppler effects, and the Doppler effect determines the bandwidth of your experiment and therefore also the time scale of the dephasing. So if you think about this excitation as a so-called Rydberg polariton, it will have a dephasing time that is given by the atomic motion. And if you have atoms moving at rapid speed, like 300 meters per second or so, as you have it in a vapor cell, then this dephasing time of that polariton is on the nanosecond time scale. And therefore, your experiment has to be faster than that. You have to be faster than this decay of the Rydberg polariton, such that you can actually produce it and bring it back down to the ground state, okay? And that's the big difference between this experiment and the experiment that I showed you in Alex Kuzmic's group, where everything could be done, let's say on a 100 nanosecond time scale or even microsecond time scale would be sufficient to do it, yes? So if you want to use the Rydberg blockade, you have to be faster than the atoms move. That's the take-home message. And for this kind of application, you have to use nanosecond lasers, and therefore the bandwidth is large, and your blockade potentials, as shown here, have to be clean and nice all the way up to several gigahertz, yeah, because if you do a nanosecond excitation, your bandwidth is already 1 gigahertz here, yes? Did this answer your question? I hope, yes?
Okay. Yes, he says yes. No.
Okay, good. Thank you.
Okay.
Then I can.
Yeah.
But I don't see more questions right now. Yes.
Yeah. I think.
All right. So let's move on. The next topic here will be the interaction of the Rydberg atom with an ion. Okay. Let's consider the following situation. Yes, we have again our ensemble of atoms here. And we have one way to make a single ion, and the way we do it is quite easy. Yeah, we excite to a Rydberg atom to this high-lying S state here, and then we just apply an electric field and field ionize it. Okay, then what is left is a single ion here in the midst of our cloud. Okay. So that's the way we are producing a single ion. We use the Rydberg blockade, and the way we can do it is either by electric fields or by an inverted Raman scheme as shown here. Depends on, that's an experimental detail, what you want to do. But you can basically release that electron easily, yeah, because it's so loosely bound, it's easy to get rid of that electron once you have excited it to a Rydberg state. Then you have that ion, and you can now apply a little bit of an electric field to move it, yes, to move it to the left, for example. Yeah, let's move it here. And then if we are exciting another Rydberg atom basically at the same position, or we try to excite it, then we are facing the ion Rydberg blockade. And the picture is fairly similar to the Rydberg blockade. It's only that, if, for example, if you start in an S state, you have attractive potentials, like here for n equals 100, for example. And that, you know, potential is no longer 1 over r to the 6th power. It goes like 1 over r to the 4th power. The reason being that this charge here produces an electric field that falls off like 1 over r squared. And as we have learned, the polarizability of the Rydberg atom at this position the Stark effect of the Rydberg atom at this position goes like the electric field squared. Therefore, the distance dependence of that interaction potential between the ion and the Rydberg atom at this position falls off like the square of the field, namely r to the 4th power. Yes, and basically then this C4 potential, the C4 coefficient, is just the polarizability itself. Okay, and that's what I plot for you here. And this interaction is even stronger than the Rydberg interaction because it's directly an interaction between a charge and the Rydberg atom. Yeah, it's not only a 2nd order van der Waals interaction. Okay, so if we are exciting again with a line width of gamma or so, yes, then clearly you can see that if the ion is sitting too close here, yeah, we will not be able to excite it. Yeah. However, if the ion has moved far enough away, we will be able to excite it. And that's what you can see. If you just move the ion with an electric field away, then initially you cannot excite anything because it's sitting too close. But then eventually the ion moves out of that blockaded area and you can excite it again. Yes. So here this was measured with an electric field strength of about 1.7 millivolts per centimeter, which was just there in our chamber as a stray field, basically. Yes. Yeah, so that's the ion blockade effect, and of course we can use that ion blockade now to try to keep the ion sitting still right next to our excitation volume. Yeah. And if we do that, we actually get the best possible electric field measurement. It's even better than the Stark effect measurements that we have used before, because we just optimize basically this time it took the ion to move away. Yeah? That was directly related to that stray field amplitude. And if we just try to tune our fields to make this time longer and longer, then we have the best possible way to eliminate all kinds of electric fields. And that actually enabled us to reduce the electric field in our chamber to below 100 microvolts per centimeter now. And here you can see the monitoring time in hours. You can see actually the drifts in our chamber, which are on that level. Yeah, 1 millivolt per centimeter over the day or so is what we observe in the various directions. Yes. Although we have taken a lot of caution to shield everything, that's what we have to compensate every day. But of course, you can also do some more interesting experiments. You can just excite that ion and basically drag it through that, let's say, dense cloud. Let's say we have a Bose-Einstein condensate. Then this ion will start to collide with the ground state atoms, and you can compare that arrival time on the multi-channel plate here. And you see that the thermal atoms, these are the red atoms, thermal ions that are the red ones, are dragged by an electric field towards this MCP, basically just in a ballistic way. Yeah? They just take a parabola, if you like, that accelerates them towards the MCP. That's the red data here. Yes. But if you put the BEC in the way, then the arrival times are actually shifted to shorter times. And that is due to the collisions that the atoms and the ions have had on the way out. Yeah? So that way, you can actually measure charge transport directly in a Bose-Einstein condensate, and you can measure the mobility in a dense cloud. Yes, that brings you closer to, let's say, condensed matter language, where people do transport measurements quite often. So one way of looking at these charges is also to use an ion microscope because here we only had temporal resolution. Yeah, we measured the arrival time on an MCP, but we had no way of looking at the spatial origin of these ions. But recently we have set up an ion microscope that is able to look at charges, ionic charges in a cold ensemble here that we generate. And this is actually not only a static ion microscope, but a pulsed ion microscope that can also give us high temporal resolution, which then leads to a spatial resolution in all 3 dimensions. So here you see a drawing of that ion microscope. It has 3 lenses as shown here schematically. Here is how they actually look in real world. And there's an MCP detector on the top here that is able to count single ions. And down here in that little chamber is where the cold atoms sit. And you can see the red elements are these lens elements that are basically affecting the trajectory and provide a magnification of whatever is happening down here onto our imaging plane by the MCP by about 1,000 up to 1,500. Here's another picture of that little device. It's about 1.5 meters high, and it contains these 3 electrostatic lenses that I show you here. And let's see how well this works. Here you see actually a test measurement on an optical lattice. You actually see it has a huge field of view. That lattice actually had a period of 530 nanometers. It also has a huge depth of field, actually much larger than 70 micrometers, because we are not limited as a normal quantum gas microscope by the diffraction limit of the light. We can have a very large depth of field. And with such a device, we can also measure 3-dimensional arrangements as shown here in that little movie. And the first application basically was to look at, again, the transport of the ions through a Bose-Einstein condensate. And here you see the red signal is where the ions were created without any electric field. And if you then drag them through a condensate, you actually see the scattering halo of the ions as they are scattered. It's an isotropic halo. All the collisional physics that we see here is still classical Langevin physics, but in the future, that will be different. We are approaching the quantum regime also for the atom-ion collision. Another way of doing experiments here is the following. We do a Rydberg excitation for generating the ion. Then we stop it with an electric field pulse. So we can generate an ion right in the center here. And then we check the ion blockade again. And you can now nicely see in that ion microscope that there's a fully blocked region in the center here where there are no Rydberg excitations possible in the vicinity of that ion. And if you go further out on the left and the right side, you see that the Rydberg excitation is possible again. So you can now directly in the spatial image see the blockade effect of that ion. Okay, next steps will be to observe that transport in a more systematic way. Of course, there will be also inelastic processes, some chemistry going on, and also we can use that device to look at ultra long range molecules and also the quantum regime of atom-ion scattering. So yeah, this new device, is now operational, and we are expecting a lot of new insights basically into the physics of Rydberg ion interaction. That concludes the second part of my presentation. Are there any questions up to this point about Rydberg ion interactions?
There seems to be one question. If more than one atom is under the field.
Yeah, very good question. I understand this question. Okay. Thank you. It's about space charge effects. Yeah, so if you have an ion microscope as shown here, let's go back, like here, yes, and one ion is on the way to the detector and the second one is also on the way, yes, then they can, but due to the space charge, affect each other. Now you should know that this flight time to the detector is on the microsecond scale, yes. So as soon as the ions keep a distance in time on the microsecond scale, there will be no effect of the space charge, and that's typically the case. Yes, we would love actually to be in that regime where we can photoionize such efficient with such an efficiency. Yes, so this is not a problem basically for our ion microscope. But thank you for the question. It's an important one. Yes.
There's a question on the earlier topic.
Yes.
And the question is,
yes, it's about the single photon source. I saw it now.
Yeah, okay, yes.
Yeah, that's also a very good question. I told you that there is a, let me go back. Oh, no, I cannot. So my computer crashed again. Yes, I told you there's a coherence time of that polariton on the nanosecond time scale. Yes, this means that the single photon will be only coherent on that time scale. Yes, it will not be able to extend in time coherently for longer. Yes, so that means that your pulses, the photon pulses that you want to extract, are shorter than this. Should be shorter than that coherence time. So it connects basically to the previous question that we have. That is why we are using nanosecond pulses. And the answer is yes, it's the decoherence of the thermal motion that forces us to be that fast. I hope that answered the question, but now I have, now it works again.
Yeah, there is one more question.
Okay.
Why did the ions in BEC arrive at smaller time of flight compared to those in thermal atoms?
Yes, this has to do with the experimental arrangement. The way it is done here is not the direct way as I show it up here. It actually goes around a corner, yes. And so one really needs to do a detailed calculation of all the trajectory to understand the sign of the time of flight difference, yes. I mean, the question is, why do they arrive earlier here, yes, if they have scattered so much? And the reason is this MCP is actually not sitting in that direction. It's sitting orthogonally to this. And so the ones that have freely moved out to this position are then have a larger a larger path basically to the MCP than the ones that get stuck in the BEC. So that's sort of, it has to do with the experimental geometry that we are using here.
I think I'd missed a question. The one question is, what about the detection efficiency of the ion microscope?
Okay, that's a very good question also. The ion microscope, I mean, the MCP itself can have a detection efficiency of about 80%. Okay, then you would say, okay, is this enough for measuring correlation functions and so on? And now the question is, can you improve on that? Can we make it better? Yes. And one way that we are actually right now working on to improve that efficiency is to amplify the signal by using that ion Rydberg blockade. Yeah, if you have an ion still sitting in your cloud and you are using a detuned laser that is exciting atoms to a Rydberg state only if they are very close to that ion, then you can produce, where you had initially one ion, a second one. Yes, and then of course the infidelity to detect one or one of these two is reduced, yes, by 1 minus p squared in that case, yes. So if you have a little preamplifier, if you like, in your excitation scheme, then you can boost that quantum efficiency of the detection efficiency of your detector quite dramatically. So there is a natural technical limit by the detection efficiency of the MCP itself, the multi-channel plate, but we already have ideas to circumvent that limitation. Very good question. Thank you. Mm-hmm. there are more questions?
I think that's all.
Okay, good. Then I should move on. Okay, so the final part of my talk, oh, but now I see there are only a few minutes left, okay, is about the Rydberg chemistry. So that's about the interaction of Rydberg atoms with ground state atoms, okay. You know that the electron is of course bound by the ionic core, by the Coulomb force, but then the electron can also interact with this ground state atom here, yes. And we will see that this gives rise to a new binding mechanism that is actually different from the ones that you typically read about in your chemistry textbook. It's neither ionic nor covalent nor van der Waals. Yes. And historically, this has, you know, it's a pretty interesting history. Yes. If you go back to the 30s in the last century, yes, where people did Rydberg spectroscopy, you know, with old-fashioned spectrometers, photographic plates, and so on, then you can see already a Rydberg series in these photographic plates here. And you can see that they have done these experiments with buffer gases actually in a discharge lamp. And if you look at the Rydberg line shown here, then if you put the buffer gas, they saw that this line is actually broadened and also shifted, in this case, downwards, okay? So they have analyzed in these papers, you know, by Amaldi and Segre in 1934, that if you increase the pressure, then that shift is increasing, yes? And it does not depend on whether you do this Rydberg experiment with potassium or sodium. It only depends on the electronic state, or on the electron. That's what it wants to say to us, yes? And then basically this slope here is different for different buffer gases. They did it with argon, nitrogen, helium, hydrogen, and so on. And they saw there are different values for that pressure shift. It's a pressure shift, basically. Now, the interaction, we are already familiar, is the interaction of the electron now with a polarizable buffer gas atom, for example, a ground state rubidium atom. And it goes like we have already seen, polarizability divided by 2 times r to the 4. Now, in the context of the explanation of that experiment in 1934, yes, the other Italian guy, Enrico Fermi, who was then still in Rome at that time, was explaining this finding of his colleagues by introducing scattering theory as we know it today. Yes, he introduced the concept of a scattering length, AS here, and the concept of a pseudo potential, which you know, has a form of a delta function essentially, with the prefactor that gives the strength of that, and that is the scattering length. Okay. So, you know, the interaction, the range of the interaction between the electron now and the ground state atom in units of the Bohr radius is a few tenths, yes, 18 in this particular case. And so that gives rise to those different shifts here, yes. So there's a well-known effect, a pressure shift that we know since many, many decades, yes. Now, the question now is, what happens if we not only look at the electron, that's what we look at if we do the spectroscopy, but if we also look at the ground state atom. So what happens to the ground state atom? And there was this paper by Chris Green, Dickinson, and Hussein Sadikpour in 2000 that was predicting that there should be a new bound state if the ground state atoms are actually trapped inside these potentials here. Yes, here you see a Rydberg wave function. That's the Rydberg electron density with its nodes and so on. And then that's the electron density multiplied by the scattering length with these prefactors gives a potential for the ground state atoms. And if you quantize that, you end up with vibrational states that you see in these potential wells. Yes, and if you now do spectroscopy and you have a good resolution, then you should be able to resolve those vibrational states here. Okay. Now there's more theory. Let's look at the spectra. Here you see a Rydberg spectrum around this 36S state, and you see on the red side here, on the left side, there is a lot of structure. And this is exactly the vibrational spectrum of these Rydberg molecules. Yes. Now, there are lots of different mechanisms at play that give rise to these discrete levels here. I don't want to go into the detail due to lack of time, but I do want to tell you that if you now put these atoms in these states and you measure, for example, the binding energy of that ground state here, and you change it as a function of principal quantum number, then of course, as you are increasing the electron density here, yeah, you just reduce the size of the orbital with the radius goes like n squared. Therefore, the volume goes like n to the 6th power. And if you look at the density actually increases with n to the power minus 6. And that's exactly the power law that you can observe here in the binding energy of that ground state of a ground state atom that is sitting in that Rydberg orbital. Now, if you look more carefully at the spectrum, then you can sometimes also see a peak at exactly twice the binding energy. And that happens at high density. And that means there's not only one atom sitting here, but there's a second atom sitting here that is also bound. And that would be a trimer. And we can measure all those trimers. And of course, if you continue that and you plot it now in a logarithmic scale, you can not only see trimers, you can also see higher polymers, if you like. And if you then increase the principal quantum number, then the binding energy of those states basically reduces. And what you are left with at high principal quantum number is again just an unresolved spectrum, because those vibrational states are sitting so closely spaced together that you end up with a pressure shift and broadening, just like in the old days by Amaldi and Segre. Yes. So this stuff up here at high principal quantum number is not really new. Yeah, that's the physics of the 30s. But if you go to lower principal quantum number, you actually start to see that there are these vibrational states, and you can study them and do all kinds of molecular physics, study the alignment, the Stark effect, and so on. We have done all these kind of studies. But there's a smooth connection between looking at dimers, trimers, and tetramers here to the shift, at higher lying quantum numbers where this binding energy, where you cannot resolve basically these vibrational states anymore, and you go over to that old shift basically in a pressure shift in these discharge measurements. Okay, I'm just checking my time. I think my time is up. Is it right?
Yeah, I think
more or less, yes. So let's look at the outlook of that part. Of course, I showed you that with this, Rydberg ground state interactions, you can generate new molecular bound states. The electron wave functions have funny shapes, as shown here. That's very nice. You can do not only two and few body physics, but you can also do many body physics. These molecules do have a very large permanent dipole moment, which is interesting. For example, you could use these molecules to dress a dipole moment to a normal atom and thereby generate dipolar physics. And of course, there's also many-body physics involved. If you are now exciting a Rydberg atom inside a BEC, one question is, do these interactions generate phonons? Can you investigate phonon-mediated electron-electron interactions in the presence of a quantum gas as a background? Or can you, like shown in this simulation, even image a Rydberg wave function of a single Rydberg electron by the back action of the electron on the atoms? Can you do Rydberg quantum optics? Well, Vladan will talk about this. Or can you actually generate experimentally circular states that where the electron is just orbiting around a positively charged Bose-Einstein condensate? These are just some fancy questions that I want to pose at the end. And thank you for your attention at this point. And I'm asking for more questions about the content of that lecture here. Thank you.
Okay, so thank you very much, Professor Pfau, for this really excellent talk. And I'm sure we all look forward to your next lecture. So, yeah, I guess there is...
Yeah, we had already a lot of discussion.
Yeah.
The next speaker is already waiting.
Yes. I guess.
Maybe now, is there something now?
Yeah, so I don't know if there's time for one question or something. Okay. Or shall we move on to the next?
I think we can move on.
I have a small question, if that's okay.
Okay, yes.
So have you detected these dimers or trimers using your ion microscope or?
Not yet with the ion microscope. No, not yet. We have not seen the spatial structure yet, but we are working on this right now. Yes.
And what is the interest in this kind of like tetramers or trimers? Are there like fundamental questions that can be answered by looking at these trimers or tetramers? Is there any?
Yeah. So I mean, from the molecular point of view, molecular physics point of view, you would like, for example, to see dynamics in these molecules, how they are dynamically responding. For example, seeing wave packets that are oscillating. I don't know whether you consider this a fundamental question.
Yeah.
But there are also more deeper questions about this molecular physics concerning the Born-Oppenheimer approximation that we always assume here, but at some point, this Born-Oppenheimer approximation actually breaks down. Yes. And then we could look at what actually happens with this microscope to see, this breakdown of the Born-Oppenheimer approximation. That's of interest for molecular physicists, of course. Yes, if you are more a many-body physics person, then I would say what is most interesting for you is the Rydberg dressing of ground state atoms with molecular states. Because not only can they have dipole moments, they can also induce 3-body or 4-body interactions. So interaction terms that are not easily accessible by other means, let's say.
Okay. Thank you very much, Professor Pfau.
Okay, so this brings us to the end of the first lecture. So once again, Professor Pfau, thank you very much for a really excellent talk. And as I said, we all look forward to your next lecture.
Yes, see you on Wednesday then.
See you then. Thank you so much.
Bye-bye.
Yeah.
Bye.
Thank you. So we take a short, maybe 5 minutes break, and then we'll join for the next talk by Professor Nagerl.
Good evening, Professor Hans. Can you hear me? I think your microphone is muted.
Can you hear me?
Yes, sir, we can.
Hello?
So,
Okay, very good.
Yes, sir. So, yeah, so please share your screen. We'll check your slides. Yeah.
There we go. Good work, yeah?
Yeah. Yes, perfect. Yes. Thank you, Professor.
Bimalendu, you need to unmute your mic.
Okay. Hello, Christoph. How are you?
Hello, you.
Yeah. Is everything going good at Innsbruck?
Everything okay, yeah?
Nice.
I mean, things could go faster, as always, but yeah, everything is fine, yeah. We're actually moving into a new laboratory right now, yeah? I mean, finally, yeah? You might remember the planning
Yes.
stage, yeah?
Yes.
Yeah, finally,
And
yeah.
what about the exhibition mod?
It's still around, but actually at the moment nobody is using it, but it's still where it was before, yeah. And I think we need to fire it up at some point. But with Corona and nobody being around at the university, it doesn't make sense to run it, yeah, at the moment, yeah. No students, nobody is looking at it. Just the researchers, yeah. But all the young students are. Unfortunately, yeah, the semester is essentially all online. So, yeah. Yeah. So, are you the chairman? Boda, are you the chairman?
Yes.
Okay, very good.
Yes.
Okay,
I think
good.
we have to wait for 2 more minutes and then we can
Oh, sure. No, we wait. Yeah. Okay, very good. Yeah. Okay.
Would you like to take questions in between your talk, if there is any question?
Yeah. Let's do the questions in between. Yeah, that's fine. Yeah. You can interrupt me if you see something. I know from talking that it's hard to look at the chat at the same time. Sometimes this works, but sometimes from my online lectures, it's when one talks, it's a bit difficult to do multiple tasks at the same time. Yeah.
Yeah, I will take care of that.
Okay, sure. No, I'm very. I mean, that's a school, right? It's not a conference at that. Yeah. So. Yeah, I'm very happy to take questions. Yeah.
Yeah.
So, Bimalendu, how are things in Delhi?
It's not very good actually. It's very bad. But hopefully things will get better. What about your place in Mumbai?
Yeah, it's under lockdown.
Yeah.
More or less. Yeah.
So lots of cases inside campus also.
Achha.
Yeah.
Yeah, it's bad.
Yeah, we are waiting for a postdoc from India, and she was actually she had a booked flight, and then 2 days before she was supposed to leave, she couldn't leave anymore because of the lockdown. Yeah, so she's trapped now, and she will hopefully get to Innsbruck in a few weeks, or yeah, I hope it won't take too long. Yeah. But the reason being that she could not enter. Yeah, I mean the plane was still flying, but they would not allow her to enter via Germany. That turned out to be a problem.
Okay.
Germany and all the flights from India, which yeah, okay, we can discuss whether this is reasonable. I thought it was stupid, but yeah.
but the flights are going to Amsterdam, for example. One of my friends traveled, I think, 2 days ago.
Yeah, but then she has the problem how to get from Amsterdam any further, yeah, and that was also, yeah, we looked into options flying into other countries, yeah, but all this didn't work on not within 2 days, yeah.
So Bodhayita, I think we can start now.
Okay. So yeah, so this is a great pleasure for me to introduce Professor Hans Christoph Nagerl from the University of Innsbruck. So a little bit about his career path. So he started studying mathematics and physics in the University of Göttingen in Germany. And then he joined the group of Professor Rainer Bloch for ion streams for quantum computation. And then he moved with the whole experiment to Innsbruck. And after completing the PhD, he moved to University of the California Institute of Technology in the group of Jeff Kimble for doing postdocs. So there he trapped single atoms already inside optical cavities, and then he came back to Innsbruck again, and then continued research work using neutral atoms. And he was one of the first to produce the Bose-Einstein condensate of cesium, and then did enormous number of work on strongly correlated quantum systems using 1D, 1D system that's using 2D optical lattices. And then also did a lot of nice work on producing molecules. So taking 2 alkali atoms and then producing molecules from them, studying different kinds of scattering experiments. And then he became a professor of University of Innsbruck. And in this part, he also have received a lot of awards, fellowships, and grants. To name some of them, the Millikan Prize Fellowship from California Institute of Technology in 1998, and then in 2003, Start Prize from Austrian Academy of Sciences to start his, the first research group, and then Rudolf Kaiser Prize in 2010. And then ERC Prize from European Research Council again in 2011, and 2017 one of the big prize. I think this is the biggest prize in Austria. That's the Wittgenstein Prize, and then the ERC Advanced Grant in 2018. And he also received another, the professorship position in Australia. So that's in another fellowship from Australian Laureate Fellowship. So yeah, and at the moment he has very nice labs on studying like 1D quantum systems and molecules for both bosonic systems and fermionic systems. And he's also very much involved in not only doing research inside the lab, but making this research popular and telling what we are doing in the lab to the people, on not only to the research people, but to the politicians, to the film industry. And when I was in his group, he sent me to some place, this European forum, where it was very nice to speak to politicians and film director. They wanted to know what we do with atoms in the lab. So with that, I would like to invite Professor Hans Christoph Nagerl. So floor is yours. Please go ahead.
Okay, thank you very much for this kind introduction, Boda, and thank you everybody for having me at this interesting workshop. Certainly, I wish it was in person, and I totally agree with Tilman Pfau, who said that these workshops live off the fact that you meet people and you talk directly. This is not possible, unfortunately, and I know how the situation is in India right now. Here in Austria, it's a bit better now. In fact, we are talking about a lot of relaxations already starting next week in view of all the vaccination going on here. Anyways, yeah, so feel free to interrupt me then at 20 minutes or 25 minutes for all the questions. I will actually start with a rather broad introduction, and I think the real interesting things only come later, yeah, and in my second lecture. So, as you can see from the title of my talk, I will be focusing on molecules, and in fact on molecules at ultra low temperatures. And in this series, in the school, as you know, we will have also other prominent speakers that will continue this and tell you about their very nice results. So, but before I start, let me briefly tell you where Innsbruck is. Perhaps some of you are not aware of that. First of all, Innsbruck is in Austria. So Austria, as you can see here, is sandwiched in Central Europe, sandwiched between Germany to the north and Italy to the south. It's not too far away from Munich and Salzburg. Salzburg, as you know, the hometown of Mozart, for example. Munich is famous in science, for example. In the old days, for example, Sommerfeld worked there. Vienna is quite far away. It's on the other side of the country. Sometimes actually Munich is really a lot closer, or even Switzerland on the western side. Innsbruck is actually where Austria is very narrow, just 50 kilometers across. So you can almost walk basically on one day from the German border to the Italian border. And Innsbruck is here at this intersection right inside the Alps. It's one of the few cities inside the Alps. And you can see from the picture above here, where you see the river. Actually, it's Innsbruck. It's the bridge across the Inn River. So this is the river, and you see the mountains in the back. And in principle, such a picture here with snow on the mountains, you can have in principle any time of the year. It's unlikely in July and August in the summer, but it can happen anytime. Anyways, it's a natural place to do ultra-cold physics for various reasons. Actually, in Innsbruck, we are very fortunate to have these colleagues in our faculty. In fact, Rainer Blatt, with his ion trapping group and quantum information group, was the one who brought me to Innsbruck a long time ago. I actually later joined Rudi Grimm as an assistant more than 20 years ago, and we were able to set up an old ultra-cold lab with various elements that we were able to condense in Innsbruck for the first time. But I should really highlight Peter Zoller, our theory colleague, who has been very active in the field. And in fact, Peter has been one of the pioneers in quantum optics and related fields, as you probably know. In fact, Peter Zoller and his team, they were the ones who formulated a lot of the very influential proposals in our field, if not in all of recent physics. Let me even say that. Yeah, if you look at how many citations these proposals have gotten, it's actually quite amazing. And some of some of these proposals you probably know, if not all of them. Let me highlight a few. For example, the proposal to use trapped ions for quantum communication. So this was actually the first proposal to propose a realistic gate operation on in this case on cold trapped ions. And actually that brought me into the field, because it turned out that my advisor, Rainer Blatt, then said, well, this is your PhD topic, you do this. Well, we didn't do it during my PhD. Another seminal proposal a little later was to use cold atoms and optical lattices to study many-body physics, in particular the superfluid to Mott insulator phase transition. And in fact, this is a workhorse in my group. We are using this every day, and it's really important for us. And we are very happy that there has been such a drastic development in our field. Well, then there are other proposals that you probably know about. For example, on dipole blockade, what we just heard from Tilman Pfau. Also here, one of the main proposal came out of Peter Zoller's group, and also as we will hear about, dipolar gases have been a very prominent topic in the local theory group. But this brings me to actually a proposal that I in particular was fascinated by. I mean, I was fascinated by all of them, but certainly in the lab, you can't do everything. Yeah, you can only run certain things. And this is the proposal from 2002 by Dieter Jaksch, who was, I think at that time, he had just graduated from Peter's group. And he proposed how to create a BEC of molecules by going via atoms and dynamically melting a Mott insulator of atoms. Actually, I'll come back to this later. That's why I already want to bring it up here. And in fact, this proposal fascinated me nearly 20 years ago. And at the moment when I had my own funding, I said, well, I want to do something like this. Yeah, and you will see why I'm so enthusiastic about this and why I like this so much. Yeah, even though this is certainly a very complicated and difficult route that we've been taking there. So, in fact, Peter, with his proposals, certainly opened a lot of research directions. And let me just remind you of what we are talking about, yeah, about some of the basics, yeah. So real materials, and I think it's fair to say that a lot of that, what we are all interested in, you and I, is understanding real materials, yeah, working with real materials, building novel materials, but going into the real world at some point and perhaps building a real quantum computer that is where you perhaps do not need to do laser cooling, yeah. Anyways, so in electrons are our favorite carriers of charge, as you all know. They are easy to transport, as you know, and they show peculiar properties at low temperatures like superconductivity. So these move through the potential of the ionic cores, and that gives rise to many interesting effects that we all love in physics. Yeah, I don't even go into any of the details here, certainly. Yeah, with atoms. Yeah, okay, perhaps say effectively this potential, to a good approximation, looks then sinusoidal, and certainly there is very rich band structure and so on that makes life of a physicist interesting. Yeah. So now in our case, we don't take electrons for obvious reasons, but we take atoms that see a laser standing wave here in the simple situation, just in 1D comic here that I'm drawing here. And our electrons are the atoms. Yeah. So atoms that we laser cool. Yeah, we'll come back to that. And so we emulate the situation of our electrons by creating an optical lattice, a crystal of light, through which our atoms or even molecules perhaps can move or should move. And we'll see very nice results from these colleagues later on, from Tilman, from Esslinger, Bloch and Esslinger and Martin Zwierlein. Yeah, so Immanuel Bloch and Tilman, Esslinger and Martin Zwierlein. So now this is the situation that we are interested in cold atom physics. Yeah, and what do we gain and what do we lose when we do this? Yeah, why do we do this? Yeah, apart from having a lot of fun in the lab and doing textbook type quantum mechanics experiments, I can really say this. I mean, that's what we, and in particular our colleagues, are doing. Yeah. So first of all, the system is greatly magnified. Yeah. So we have optical lattices and not angstrom length scales. So we have the possibility to detect particles individually and also to directly measure the momentum distribution and so on. So there are lots of advantages by this very strong magnification. Then everything is slowed down. Yeah? Atoms are much slower than electrons. The entire dynamics is much slower. And so the advantage is that one can see processes without going into, with doing a lot of effort. So for example, we don't need any femtosecond lasers to probe the dynamics of our particles. Yeah. So this is an advantage, but on the other hand, this is also a disadvantage because slow dynamics is related to reduced energy scales, and that means actually very low temperatures. Our Fermi energies, to give you a number, yeah, in the order of microkelvin and not in the Kelvin regime. Yeah, so we need to go to very low temperatures with these atoms, and that's what we call ultra-cold quantum gases. And that's actually only possible because we can laser cool. And even then, we are not really, as you know, in the low temperature regime. Yeah, so this is a drawback to some extent. Yeah, but on the other hand, it turns out that that there are some workarounds. Yeah. And then also a drawback using atoms is that interactions are at least in most cases, they are local. Yeah. So short-range van der Waals interactions, basically contact type, delta function type interactions. And so we need to do tricks to do to obtain long-range interactions. And Tilman, Pfau just told us what to do, what one option certainly, yeah. And but it's evidently not trivial, even though there's a long history of doing, for example, Rydberg systems, as we just heard. But doing Rydberg systems plus many-body physics and plus having all the ingredients that you wish is certainly not easy, yeah. So what platforms are there to solve this problem of missing long-range interactions? Yeah. So actually a very popular platform is by now ions and ion traps. And with ions and ion traps, you can in fact to some extent engineer interactions between the ions. You can actually engineer the decay of the interactions as a function of distance. And so just a disclaimer here, I'm listing some places where people are doing this work. I'm certainly primarily been listing the people that are part of this conference, and there are many more by now. And I hopefully I don't I'm not doing I'm not doing anything bad to anybody. So, and this picture is actually taken from the Innsbruck group, yeah. And we'll see nice talks what you can do with ions and ion traps later on from our friends Christian Roos and Stefan Village and Didi Leibfried. Now, then there are atoms in cavities, yeah. So interactions mediated by the photons in the cavity, and I think Tilman hasn't put his abstract online, but I'm pretty sure that he will talk about atoms and cavities. And this image is taken from Vladan Vuletic groups and their experiments in various places apart from Zurich, at MIT, Stanford, Hamburg, Berkeley, you name it. Yeah, so that's also an option, and you will see in the school, I'm sure, very nice results on that. So now the next possibility, and Tilman Pfau already mentioned that briefly, that he will be talking about it, is to use dipolar atoms, specifically magnetic dipolar atoms, to use or to make use of long-range interactions. Yeah, so this has been done in Stuttgart, for example, in Tilman's group, and in various other places. Also here in my colleagues' group, Francesca Ferlaino's group, and there are really nice results from various places on dipolar atoms. And finally, this list here is Rydberg atoms, as we just heard about. Here I'm showing an image from the Caltech group with Rydberg atoms trapped in tweezers. We'll hear about that apart from what Tilman already said from Vladan Vuletic, and there are various places where Rydberg atoms are being used. And here I highlighted the ones there where the many-body aspect is sort of the dominant drive. So these are 4 platforms that you all know about, and we'll hear about many of these platforms in this audience, in this school. Yeah, and what else is there apart from other options? Certainly, this list will not be exhaustive. I think I'm just listing my preferences, is also the school's preferences. So it's actually polar molecules. Yeah, polar molecules here take dimer molecules, and it's indicated here, composed of 2 atoms, and these can interact via the electric dipole-dipole interaction in this characteristic way. The pre-constant CDD, with D being an induced dipole moment. You actually polarize the molecules in the lab frame with an external electric field or by applying AC fields. And then the interaction is falls off as R to the 3rd power, and there is an angle dependence, assuming now here that all the vectors are aligned in the same way, but you can actually now rotate them with some angle. So there is an angle dependence. And we will see very nice results from Juni and Martin Zwierlein later in the school. Yeah. And their experiments at Gila, in Innsbruck, at MIT, Durham, and many other places by now. So polar molecules are one platform, one alternative platform. Now I've shown you 5 platforms for playing with long-range interactions, and it's hard to give a preference, but let me just, and certainly all of them have yielded very nice results, and I'm sure will in the future yield further very nice results. Let me just state the advantages of polar molecules. And I see there are questions in the chat. Let me actually do the advantages and then come to have a brief, quick look at the questions. So, so the advantages of polar molecules are, the interaction is relatively strong. Yeah, it's certainly not as strong as what we've just seen from the Rydberg systems, but in comparison to magnetic dipolar atoms, yeah, so ground state atoms, they are comparatively strong, and that's certainly an advantage. Yeah, so one perhaps not in all cases has to go to the very lowest temperatures. In the end, actually, that's what we do or try to do, but perhaps later on this can be relaxed a bit. Yeah. Then this interaction is tunable, yeah, by either by how you polarize your molecules. That's a nice feature. Then there is an angle dependence, as I just mentioned. Then all the control techniques that have been demonstrated on atoms, ultra-cold atoms can, and I don't see any no-goers here, can be extended to molecules. Yeah, not everything has been demonstrated, but by now I would say a large fraction of these techniques has been demonstrated. Then dipolar molecules are long-lived. Yeah, what do I mean by this? I will come back to that later. But when we just have them, let's say, in a trap and in a lattice, for example, where they collide, we and the community has demonstrated that these molecules live for a very long time, so they don't decay. Yeah, so decay due to blackbody radiation or so is negligible. So that's for some experiments this is an advantage. Yeah, and then certainly next we have to discuss what happens when these molecules collide, and then perhaps there are relaxation processes and they will effectively kill these molecules. Yeah. And and actually the last sentence here, the last point brings me to what I think will be the future soon, that one is actually able to form molecular superfluids. So a Bose-Einstein condensate of dipolar molecules with rather strong interactions. As we will hear in this workshop, we'll hear about supersolids and Bose-Einstein condensates of dipolar magnetic atoms, but with rather weak interactions. And we could hopefully be in a regime where interactions are really strong. So an open question I already said at this point is, can we form a Bose-Einstein condensate of molecular dipoles? Yeah, and when I compare to Rydberg atoms, I'm not saying that Rydberg atoms cannot be brought into a state of a superfluid. Who knows? Yeah, I'm very careful here, but for sure it's not easy. Yeah, so perhaps one can do other types of excitations on Rydberg atoms into the state of a BC, but it's not so easy as with dipolar atoms, and I think with dipolar molecules this will be possible. Certainly there are also challenges, yeah, or difficulties, yeah, if you want to see it on the negative side, but I will call it challenges. Yeah. So first of all, molecules are not readily laser coolable. Yeah, there are exceptions that I will briefly mention later on. So that the technique of laser cooling cannot be, at least to almost any molecule, cannot be applied. One has to say, on the other hand, with atoms, it's not too much different. Only a handful of atoms can be well laser cooled, and with many others, it doesn't work. Yeah, but certainly the field of molecules is much richer than the field of atoms, and the class of molecules that can be laser cooled is rather narrow, even though they are very nice developments lately. Then the next question is about stability. Yeah, so the field of ultra-cold atoms lives off the fact that ultra-cold atoms are stable. Yeah, so when I talk about stability, certainly I mean systems that are sufficiently dense, interacting systems, and systems that we want to trap and where we want to see interesting interaction effects. And with atoms, it has turned out, yeah, I would say 30 years ago it wasn't clear, but became clear due to the experiments in the 90s that Bose-Einstein condensates are sufficiently metastable that one can actually produce, so atomic Bose-Einstein condensates can be made in the lab. Then another challenge is connected actually with this is scattering of molecules. Yeah. So what is exactly happening when molecules scatter? And for example, if you had a chemical reaction in the background that can happen, what does that actually, how does that affect your stability? Or even if you don't have that, if per se molecules would be stable under two-body processes, can they still effectively collide inelastically? So this is in fact still over years now has been a debate, and it's not really clear, and we've, I would say, still not really seen the final experiment on that. Yeah, so this is a challenge, and it's an interesting challenge. And then finally, molecular preparation strategies are comparatively complicated. Yeah, so we've seen Tilman Pfau's experiment in vapor cells, which are where we can see quantum physics at a very basic level already with rather little infrastructure. Here with molecules, certainly we have to go through quite some effort, at least the way we do it. Yeah. Perhaps we like to do it difficult, yeah, but in a difficult way. Okay, anyways, it's a double species setup, and we detect usually via the atoms, via the molecules. It turns out to be advantageous. So we have to pull all the tricks of cold atom physics plus some additional molecular control tricks to make this thing going. Yeah, so there are challenges. Yeah, and but that keeps us happy that we have challenges. So let me have a quick look at the chat. Okay, I think there's no question relates to me, yeah. So I can actually continue for a moment, yeah. And Borda should interrupt me once there are questions, or we should stop for questions. So
yeah,
now,
so far there is no question.
Yeah, so people should raise their hand or put something in the chat, but we are just at the beginning of my lecture still, certainly, yeah. So, so what is the goal in my group and perhaps in some other groups? Yeah, to prepare samples of molecules that have where the density is such that if you think about a lattice potential, we have something on the order of unity filling. Yeah, so this is sort of the goal, and I'm totally happy if we do this in 2D, yeah, as indicated in this comic, but perhaps we can also do more, do layered system or something else, yeah, or even 3D. And actually, Jun Yi will talk about that surprisingly that molecular dipoles in a dense regime can be also stable in the 3D setting. Yeah. So this is certainly a comic here. This is my dream that I have been dreaming about. And what are the applications? Let me jump ahead a little bit already, yeah, to see what has been my motivation for many years. Yeah, so I'm writing down here some Hamiltonian that most of you probably know, but let me just walk you through this and remind you. So I'm writing down a Bose-Hubbard type Hamiltonian where I'm adding an additional term. Yeah, so what we are up to is to do Bose-Hubbard physics and generalizations of that with dipolar molecules. And I'm writing down, let's say, the simplest Hamiltonian I think that you could write down, and you can think about more interesting situations certainly easily. Yeah. So what is this? Yeah. So it actually, you see three terms. Yeah. And usually interesting physics happens when two of these energy scales set by the prefactors J, U0 and U1 here. I'll walk you through what I mean by this in a second, when they become equal. Yeah. So it could even all three can become equal. Yeah. So that's usually the situation. Very, very generic. Yeah. So what is this actually? Yeah. So this Hamiltonian, in the spirit of what Peter's group suggested a long time ago, describes the dynamics of our atoms on a lattice. Yeah. So like electrons in the crystal lattice. So we have the tunneling processes here in the first term, indicated here with this little comic. We have the local interactions, the on-site interactions, and I should already say here that that certainly that includes also the dipole-dipole interaction that is that gives also rise to a local contribution. And so these two first terms that and you all know about this have been very rich already, and various groups have played with this now for many years, in particular also our group. Yes. So already these two terms are very interesting, yeah, and it has given to rich physics. And now we want to add a term that's a next neighbor interaction. So these brackets actually indicate, as here on the left, that this is interaction. I and J are the sites next neighbor. So not on sites, but the neighboring sites. And there's an energy scale related to that. And in fact, it turns out for molecules, dipolar molecules, this is actually a rather large number given the typical temperatures in such systems. Yeah. So there's a nice review on all this beyond Bose-Hubbard physics or beyond the standard two terms physics. And in fact, in Innsbruck, there has been an experiment in Francesca Ferleino's group already a few years ago, seeing first indications with magnetic dipoles of this third term, sort of, yeah, in a nutshell. Okay, so this is our motivation, and what actually is possible with this Hamiltonian, yeah, and there's certainly there's been a long history and various proposals what one can do, and one can do at the characteristic phase diagram and the so-called mod lobes in under such a setting, yeah, where you have a non-zero nearest neighbor interaction. And here this diagram shows is plotted as a function of the chemical potential and the tunneling rate for fixed U1. And the outside area is the standard superfluid in the lattice, and then one can have half filling, a third filling, and quarter filling, for example. So interesting many-body phases, even though this is just a static setting, that go beyond what we know from contact interactions. Yeah. Unless you do some tricks, yeah, with fermions and higher order processes, but and very low temperature. So the dipolar interaction makes this phase diagram more interesting. And in fact, we'll hear a bit about this also in this workshop, is that there are new phases sandwiched in between. SS stands for a super solid phase, a lattice super solid, where we have where we sort of combine superfluid properties with non-trivial correlations, spatial correlations. Okay, so this is one motivation for doing this. Yeah, let me give you just two others, just that you know. Actually, they're totally different in spirit. Yeah, one is in fact indicated here on the right, and just took the picture from one of these publications. It's shown dipoles on a lattice. Frozen on the lattice, so no motional degrees possible. Yeah, so in principle you could do this also with other platforms, let's say the Rydberg platform, but that's for sure a very nice possibility. We have to talk about what would be the spin. Yeah, we have rotational degrees of freedom, for example, in molecules, and then you have some spin-spin interaction that is sizable from one side to the other. Yeah, so I'm listing here some of the relevant literature on that. And in fact, in Juni's group, there have already been some experiments along these lines. So that's what we could call frozen spins. Admittedly, I have to say, I think the interesting part is where we have everything. We have spin degrees of freedom and we have motional degrees of freedom. I think that takes us closer to real electronic systems that in the end we are interested in. And then a bit more perhaps exotic are systems indicated here, where you have layered systems, where then you can have interaction from one layer to the other, and where where you can form, for example, interesting strings that bind or unbind, depending in this case on the distance between the layers. But it could just be that you modulate the interaction strength, and you then see phase transitions between strings and melting of this string phase. Okay, so there are proposals, for example, by the theory group in Stuttgart from Hans-Peter Büchler. So this is interesting physics, and I think one could give an entire lecture about all this. I'm an experimentalist, so I won't do this certainly. Yeah. So, but just one more motivation. So if you had a 2D system like that with spins like this, yeah, and already what I'm fascinated by is the fact that you could, in principle, do local control, yeah, local flipping on this of the spin here, and then look at how this excitation propagates in your system. Yeah, so something which is very hard with electrons to do, what with molecular dipoles one can do this, or actually with the Rydberg platform, I think there's also a good chance. Yeah, but again, it would be interesting to have also the motional degrees available. Yeah, so this is a bit similar to what you could do in a 2D ion trap, for example, or with at some point. Yeah, it's not been demonstrated yet that this could be done, or with a Rydberg system. Yeah, and I think 100 by 100 particles are realistic in these various platforms. Yeah, so I call this a molecular quantum simulator. Yeah, so now comes the main question: how do you prepare such a system? Yeah, how do you go about? Yeah, and the trick that we've been trying to look at is actually, or what they've been using is to do all the control on the atoms. Yeah, so we have molecules that are actually dimer molecules. They're made out of 2 atoms, and we do all the laser cooling, all the entropy removal on the atoms, and afterwards only quote unquote maintain phase space density. Yeah, so that's the idea, and in fact, a big advantage when you do all the control initially on the atoms, and I'll go into more detail certainly a little later, that you inherit the control over the external and internal degrees of freedom, including hyperfine degrees of freedom from the atoms. Yeah, so we know very well how to do this on atoms. Can we map that onto our molecular sample? Yeah, so then you can ask, why not differently? Why not laser cool, direct cooling techniques? Why not use something else, dipolar atoms or Rydbergs? Well, I gave some answers already partially, and later on some of these things will become clear. Yeah, but I think you see already my motivation why we want to do this on molecular dipoles. So just for the history, this activity started getting serious more than 10 years ago here with this work from Juni's group at Gila with KRB molecules. And in Innsbruck, we have been working primarily with rubidium cesium molecule, and then other groups stepped in. And I think this is a really nice and friendly competition, Durham, MIT, Hong Kong, and other places, yeah, Hanover and so on, Munich, and so on. So this is still my introduction. Yeah, I'm still doing introduction, but I think I have two hours and tomorrow 2 hours, so I think that's fine. So what is the strategy that we're using in Innsbruck? Yeah, so the idea is to mix 2 Bose-Einstein condensates. Yeah, so we have very cold samples with very high control, and somehow we mix them. Yeah, somehow. I say somehow because that's the difficult part, and I will emphasize that again. Yeah, and we've been working on this for quite some time. And then we create molecules, yeah, and ensure somehow that the phase space density remains high, that we don't lose phase space density, and this control of the molecules, actually we take all the way to the very ground state of the molecules into a suitable row vibrational state. Ideally, it's the very ground state for reasons of stability, evidently. Yeah. So that's and also because that's where usually the molecules have a sizable dipole moment. So that's sort of in 2 sentences what we do. Yeah. And in fact, let me bring this, come back to why I actually highlighted Peter Zolle at the beginning. Well, one reason was because he and his group came up with this proposal of controlling atomic samples and turning atomic samples into molecular samples in the regime of quantum degeneracy. So this is this proposal, yeah. So so basically the idea is to do this with a lattice. Yeah, a lattice helps in various ways. So the plan is to put both samples into a 3-dimensional lattice and to freeze out the motion. So turn actually these atomic samples into a mod insulating state. So a mod insulating state with 2 different species. Yeah, and so I come back to this in a second. This is the hard part. Yeah, I already say it now. Yeah, so going from 1 to 2 is sort of the magic. That's where the difficulties really arise. Yeah, turning these 2 boson-Einstein condensates in a sample of dimer, of pairs. Yeah, at first, not even dimers, just atom pairs. Yeah, so we want to create atom pairs at each side, ideally with unity filling, and then turn these atom pairs into more bound pairs that are actually a molecule. Yeah, weakly bound molecules. And then turn these molecules into ground state molecules where then they can interact when you turn on the dipole. Yeah, so indicated here by my flashing, my flashes, that now these dipoles can interact and do something, can do interesting physics. Okay, so let me actually look at the chat for a second. Yeah, I see there's a question.
Yes, Christoph, there is a question. So that is, why didn't you consider the chemical potential term in the Hubbard Hamiltonian?
Because I'm keeping it simple. I'm certainly doing it simple right now. Yes, so certainly you should write down more than that. But I just wanted to highlight the essence. Yeah, what I would find the essence of the Hamiltonian. Yeah.
So there's another point. This is just a remark. So so the talk is like 1.5 hours today and 1.5 hours tomorrow. It's not 2 hours.
Exactly. Yeah, 1.5. Yeah, when I say an hour, 45 hours, say for 45 minutes.
Yes.
No, that's fine. Yeah, that's fine. Yeah. So now I think I have finished 45 minutes at this point, right? Almost. Is that correct?
Yeah.
Yeah, a little less. Yeah.
Yeah,
after your lengthy introduction. It was too long. You have just said Christoph from Innsbruck is now starting. Yeah. Okay, good. So let me continue here. Yeah, still by introduction. I'm still doing introduction, but that was the goal. Yeah, to do a broad introduction. Yeah. So let me see if it doesn't work at the moment. No. So this step 2 to step 3. This is what we call Feschbach association for obvious reasons. You'll see later. I think this is actually we know how to do quite well. Yeah, with very high efficiency, and it's not pushed to the very limits. Yeah, when I call all these processes that I'm writing down here, we want to do this because we've done all the cooling initially. We want to do everything ideally with nearly 100%. Yeah. And as long as limited certainly by what quantum mechanics allows us, yeah. But that's probably, my guess is it's close to 100% at least in a certain setting, yeah. So this we know how to do with very high probability, and you'll see data later from my lab, and also from Juni's lab, yeah. So this works nicely, and the ground state transfer also works nicely, yeah. This transfer from weakly bound molecules to ground state molecules, yeah, where then you can switch on the dipole. Yeah, so this is actually done with a laser technique that's well known. It's been used in the field of molecular physics the other way around typically, but we're using it in the setting of cold atoms, from threshold to the ground state. Okay, and so the bottleneck actually is this first step from 1 to 2, yeah, and I will towards not today, but tomorrow then discuss this a bit more, yeah, this bottleneck, yeah. But I can already say what is the trick, yeah, that actually we worked on, and perhaps sometimes you don't need to do this trick, yeah. I'm a little bit careful here, yeah. But for the bosons, as we find, we need to pull some trick, and Giller solved this problem by mixing a mod insulator for the bosons and a band insulator for the fermions. And in our case, with rubidium cesium, where both are bosons, actually we used sort of both double mod insulator, sort of. I have to be a bit careful, yeah, because we never did this in a perfect way, yeah. So, but that's, and in fact, I can say this already now. That's what we are still working on to optimize this. Yeah. So what are the challenges? Yeah, for all this. Yeah. So the challenges are how to mix the two species. Yeah, and we'll come back to that. Yeah, in particular, on both are bosons, and fermions tend to help, I would say, because fermions, the way they repel each other by the exclusion principle, it usually leads to more stability. I think one can fairly say that. Yeah. So then three-body processes are actually a problem. Yeah. Also here the fermions might help, but if you have only bosons, you fully run into three-body processes, and you have to be either a bit lucky or do some tricks. Yeah, to avoid them. Yeah, in fact, I have to say we have not yet been able to fully avoid them, and but I think we know in principle how to avoid them. So in fact, as you all know, probably, and actually I will talk about three-body processes a little later in the second hour. Three-body processes are the first is the central processes that make our cold atom samples unstable. Yeah. So two-body processes we can inelastic two-body processes we can suppress by going to the right states, but three-body processes can be a nuisance. Yeah. You can also make them to good use, but in most cases we would like not to have them. Yeah. Yeah. And then that connects actually with the next sentence. Yeah. To suppress inelastic molecular scattering. Yeah. So turns out that most likely that molecular loss is due to an effective three-body process. Yeah, so I'll come back to that briefly later. Yeah, and then the final challenge, which is I think more on the technical side, is how to combine high-resolution imaging, as shown down here, where you have your sample and you want to put on a CCD camera and then detect the local correlations. Yeah, as indicated here on the right in my comic, to combine that with electric field control. Yeah, so you want to be close with the lens, but on the other hand, you have to apply voltages that are not negligible to polarize the molecules, and it's on the order of several kilovolts per centimeter. It depends a bit on the species of choice of the molecule of choice. So that's actually not trivial. We are working on that, and we still have not implemented the final version of what we want in the lab. Yeah, I have to say that. Yeah, we'll hear a bit more from June, I guess tomorrow or the day after tomorrow, June Yi, but also there's now not yet both. Yeah, the control plus the imaging of individual molecules that's not yet been implemented. Yeah. So okay, that brings me to the outline. This introduction, I hope it was not too simple, but I think it's good to start very gentle. Brings me to the outline of my talk. I will talk about a bit about scattering, remind you of scattering. So I'm the first one in the series to talk about scattering, I think. Yeah. And so I think I can take the luxury to talk about a little bit about one of the important tools in our field, that's Feshbach resonances. Yeah. So actually, I'm making a living of Feshbach resonances essentially. Yeah. I'm using them for making molecules, and I'm using them for tuning interactions. And then I will divert a little bit. I hope you allow this to talk about three-body physics and Efimov states. Well, this one always has to keep in mind, because that's in the end what limits us, because the rates are sizable, and if you're unlucky, Efimov states can actually greatly enhance the three-body loss rates. Yeah, so I think for most of the experiments we want to stay away from any of these so-called Efimov resonances. And then I will talk to the subject of this lecture, to the dimer molecules. First, to Feshbach molecules, then how we go to the ground state. I will divert shortly to talk about homonuclear experiments that have been done in my lab, where we've learned a lot, and then how we do this control on rubidium cesium, and how we are trying to improve this kind of control. Okay, I'm looking at the chat now. I'm seeing a question.
Yes,
okay, what is typical size of 3D optical lattice. That's an easy question. Yeah. Typically, we have in my group, we have about 50 by 50 lattice sites, 50 by 50 by 50 lattice sites, typically. Yeah, perhaps a bit more. I think one can do more. Yeah, I think what one has to do is one has to combine lattices with box traps, and it's been on the agenda in my group. The problem being, perhaps I should say that when you have a lattice, that you also, due to the finite size, lateral size of the laser beams, there is always some weak but non-negligible confinement laterally, and that shifts everything. Yeah, it shifts the entire energies through space, and that's sometimes not very advantageous. Yeah. So, but I think we can do systems. The community, we will be able to do systems with tens of thousands of particles in the end. Yeah, with in 2D. Yeah, that's my guess. Yeah, at some point. Yeah. So 100 by 100, I think, is very, very much doable. And if we work a bit harder and we can do larger samples, so that could be tens of thousands of 2D. And then the next question is, what can we do in 3D? Perhaps even more. Okay, so I'm very optimistic here that we will push this to very large systems where our theory friends will have a very hard time to do any calculation that tracks every single particle that we have, yeah, in our system. Okay, so thanks for the question. Perhaps just one comment. So in our case, with the atoms right now, yeah, we are working with array or bunches of 1D systems. And typically we intentionally work in a regime where we have about 40 atoms per 1D system. 40, so 20, that has a size, then it's about, since the lattice spacing is lambda over 2, lambda is about a micrometer. So we have a size, 40 atoms, roughly 20 microns is the size of this 1D system, yeah? along the long direction. Okay, so, but I will not talk about any of that work. We'll focus here only on the molecules. Okay, let me see if I can now go to, it took away my pointer. Okay, so now let me start gently. Also on this part, let me start with scattering. I remind you of S-wave scattering, because that's what we want to control in our experiments. Yeah, so two-body scattering at this point. Yeah. So in the low temperature regime, as you all know, it's a single parameter that tells us a lot. In fact, if you go to dipolar scattering, it will be a bit more difficult. Yeah, but in the low temperature regime, it's because you have your plane wave and you have your scatterer here somewhere. I hope you can see it in the center of the screen. This little dot is our atom or our scatterer. So it's usually the extent is small with respect to the wavelength of our de Broglie wave. And so then you will have scattering of that defect. Let me call it a defect. Yeah, so that's S-wave scattering. And since I'm an experimentalist, I like to see analogies somewhere. And perhaps you also like the analogy that I did not too long ago with my kids in a local fish pond. Yeah, so have a look. Yeah, so it turns out I try to do this in waterways often, but what helped here really that you had this shallow water level, and that you could see actually the sunlight created. You hardly see the wave, but you see it on the ground, yeah, because of the focusing of the light. Okay, anyway, so this is my little didactic diversion. Let me go further and talk about S-wave scattering. And then, as you know, in some sense, the scattering length A is a measure for the phase shift of this in the scattering process. Yeah. So first of all, it tells us something about the cross section for identical bosons. It's 8 pi times a squared in the low temperature limits, and it has a sign. It is it affects the interaction in a Bose-Einstein condensate. It sets the stability, and as you all know, for rubidium 87, one of the forces in the field. This A is on the order of 100 Bohr radii. In fact, that's the generic value that you expect. The so-called van der Waals length is on that order. Yeah. So that brings me to length scales. There's the length scale of the chemical bond, usually below a nanometer for simple systems. Yeah. The van der Waals length is on the order of few tens to 100 Bohr radii, depending certainly on the mass and the precise value of the C6 coefficient. And the scattering length then is, let's say, 100 Bohr radii, but it can be tunable in many cases. We come back to this. Yeah, this is actually why I'm doing this part here, because you can change it and you can play with it. The interparticle spacing is usually large with respect to that. And so we are always in a dilute limit in some sense. Trap size is even larger than that usually, not necessarily if you do confinement in a lattice, then we are not separating that anymore, and then interesting physics certainly happen. And the Broglie wavelength at typical temperatures, low temperatures, is on the order of a micrometer for, I think I put in here, typical temperature of a microkelvin. Yeah. So as you know, quite often interesting physics happens when these length scale compete, but the way I listed them now here, they are sort of all separated. Yeah. And that makes things sometimes quite easy. Yeah. So where does this all come from, this scattering process? Well, we don't have a delta function potential, but and I'm sure you're aware of this nice review here by John Weiner. We have a situation where we have atoms coming in, scattering on these hyperfine branches. In the end, what's behind it is certainly the hyperfine interaction that then turns into this covalent bond here with singlet and triplet states. And in fact, our goal will be to come from this hyperfine branch for some molecule all the way down to the ground state of this singlet potential. Yeah, so that's well known, yeah, and that's behind of all the scattering. These are the potentials for scattering. This shows a comic for the wave function, yeah. It's the scattering wave function here at some 1 microkelvin roughly, plot taken from this review, where you have the sine wave, and then this is modified close to the origin, and then depending on the specifics of your atom and the bound states, yeah, we'll come to that in a second. There is a certain value at the origin that can be 0. In many cases, it's positive, but it can also be negative. Yeah. So certainly the question is, can you play with this? Yeah. Can you do something about this? Yeah. Can you modify the scattering length? And if you take your favorite quantum mechanics textbook or this lecture here from Jean Dalibard with the square well potential, you know how to solve it. It's elementary physics, and you will actually, as a function of, in this case, of B, yeah, and the depth, the square root of K0 is the depth, as here in the figure of this potential, you will get what we know as scattering resonances. Yeah. So you change either the depth or you change the extent of your potential, of your square well potential, and you will get resonances. And this is well known why this happens. Whenever a bound state pops up or goes through threshold, you have a resonance. Yeah. So I'm sure you've done this, and certainly this looks nice. But how do you do this? Yeah. In any real experiment. Yeah. So in real life, neither B nor the depth can be tuned. So go back. I don't go back now to the previous van der Waals potentials that are covalent so potentials that I just showed you, and you will see that you cannot do this. Yeah, but you can do a trick. Yeah, and the trick is known as a Feshbach resonance, known from nuclear scattering, is where you have more than just one channel. Yeah, just one, not one well, but 2 wells, a second channel, and you in fact couple from your incidence channel on which you scatter. And assume now we scatter here, as indicated in this picture. You couple onto this bound state, and then you can in fact mimic the situation that you change the binding energy of that bound state. Yeah. So what do you need for that? you need two things. You need that this bound state differs in magnetic moment, because it's usually done by the Zeeman effect, this shift. And you need the coupling that I've indicated here by this dashed arrows, in this comic. Now, this is well known, and this gives rise to a resonance of this type as shown down here. The scattering length as a function of magnetic field diverges at a specific value of the scattering field. So away from the resonance, where you have some background scattering length, you have some characteristic that's dispersive, I call it, shape with some strength that's all lumped into the delta, the width of this resonance. Yeah, so this is in principle very nice. Yeah, so this is the situation here. Again, there's just this comic that I just drew on the other side. Here's a picture from this nice review paper from my colleagues, from my colleague Rudi Grimm here in Innsbruck in part. And delta is this zero offset here, indicated here on this plot. Yeah, so that's the generic situation. And I don't go into the details what actually gives rise to this coupling. Yeah, so this is hyperfine interaction, but it can also be some higher order process. Yeah, and I will just mention the result of that. I will not bore you with any of the Hamiltonians. So now, what does this bring to us? Yeah, so this is my comic. Yeah, with this bound state here in this case below threshold. Let's assume the coupling is sufficiently weak so that there's not too much mixing initially, but basically this looks like the situation that you have one bound state that you can now tune across resonance, by changing the energy of these two channels relative to each other. Yeah? And this is done usually by means of applied magnetic fields, because it's the Zeeman effect that shifts the energies. So now, so this is actually quite nice. What I just said earlier is possible. Yeah, you can in fact change, tune your bound states through threshold. Yeah. So what's the binding energy of that last bound state in the limit where the scattering length is larger than the van der Waals length? So sufficiently close to resonance. This is a very good approximation that you find in any good quantum mechanics textbook, namely that the binding energy scales as the inverse of the square of the scattering length. Yeah, and certainly I wouldn't be talking about this. We are lucky in our field because these resonances are scarce. Yeah, they happen every once in a while for a typical atom, and it's not a dense forest of resonance, but we have every once in a while, we have one of these hyperfine states that for some other channels come to threshold and cause a resonance. Yeah, the situation is already a bit more involved if you take dipolar atoms. So this is a summary of this Feshbach resonance situation. Top is the scattering length as a function of relative magnetic field. And below is the binding energy of the state. Near the resonance, you have this quadratic turnover, but away from the resonance, whatever happens. Yeah, it can look wild. In most cases, it's more or less linear scaling as a function of the magnetic field. Yeah, so these are the formulas. And away from the resonance with some differential magnetic moment, you have a typical linear shift, and this is the zoom in the resonance, and certainly near the resonance, and you can correct and be more precise at what I do here. Yeah. Okay. So that's what we want to control. Yeah. Via the binding energy, we control the scattering length, or vice versa, as you can view it. And in fact, this scattering length also here has a very nice geometric interpretation. In this limit of large scattering length, the size of the dimer is actually A/2. Yeah, so this is actually quite nice and very simple. Yeah, we call this a quantum Halo state. So okay, so now let me plot this actually as a function of 1/A. So B minus B naught effectively proportional 1/A. So it looks like this parabola that goes down here, and this is the two-body physics of this weakly bound state, of that Halo state. And be reminded, there's certainly many other two-body bound states nearby, or not too far away, and they exist. Yeah, that's a nuisance. Yeah, in some cases, and Johannes Hecker-Denschlag will talk about this more. He has really nice results on probing this, but it's a nuisance, but it's also a nice feature sometimes. Yeah. So let me just briefly highlight some of these Feshbach resonances that we have in the field. One of the very prominent ones is here shown for lithium-6 fermionic lithium between these lowest lying hyperfine states in the Paschen-Bach regime. Yeah, so in the field of already a few hundred Gauss, and there's a resonance at around 8, if I remember right, 830 Gauss. Very prominent resonance, very strong resonance, allowing to create molecules, but also allowing us or our colleagues to go over the side where there's no molecular state, yeah, on the right, but still being able to observe pairing, BCS type pairing. And so let me go back. Here's the situation of this. On the right here, we don't have any bound state, yeah, but still we can do interesting many-body physics there. And I'm sure we'll hear a bit more about this in the school, yeah. So here's the second example of a very nice situation that we love in Innsbruck. That's the case of cesium. So bosonic cesium, there is only one cesium isotope that can be trapped in the lab, cesium-133, the famous one. And there are actually in the range from 0 to 1,000 Gauss, there are essentially 3 resonances. One that is basically at negative fields, but it has its effect on the positive side here, plus 2 resonances at about 550 and 800 Gauss. So that's the situation for cesium. Please ignore the vertical line at the pole of resonance. Yeah, so this is for us irrelevant here. It just indicates where the pole is. Yeah, but what I would like to say is that the cesium scattering length on average, this is done by me by hand, is large. Yeah, so if you take the cesium atom in the lab, you will see that on average, the cesium scattering length is 2,000 Bohr radii, and that has drastic consequences. So one has to work, I already say it here, around the zero crossing here at low fields or at one of the other zero crossings, but it's hard to work at very high values for the scattering length. Okay, so this is the run for cesium, and I should say this neglects higher order resonances. So this is just the so-called S-wave resonances, yeah, where the molecule is that couples to threshold is in an S state. Here the situation is a bit more complicated. This is now the case that we will turn to later. That's partially why I'm introducing all this. This is the situation for rubidium cesium. So you see top, the scattering length between, so this is now the interspecies scattering length between specific spin states of cesium. Cesium and rubidium. I don't go into details here at this point. At top is the scattering length, and bottom are the bound states. Yeah. So this is the situation for a realistic molecule. Yeah. So let me go back. This was our comic. Yeah. Our simple situation. Yeah. One resonance, and the world otherwise is easy. Yeah. So this is a realistic situation with all the bound states, in this case higher order states also, and the zoo of resonances, effectively starting useful resonances start at about 180 Gauss and then go beyond to a few hundred Gauss. And I can already say at this point, the resonance that we will be interested in later is this resonance here around 350 Gauss at this point. Yeah, this one S resonance, it turns out. Yeah. Okay, that's rubidium cesium. Just for the record, this field of Feshbach resonances in cold atom physics has now been around for 20 years. Started with the work of the Wolfgang Catalyst group on sodium, observing a Feshbach resonance here at around 900 Gauss in an atomic condensate of sodium. And in this particular case, they saw loss, and they saw excess energy, and saw this excess energy in the expansion of their cloud. And at that time, details of what was going on were not yet, I have to say, not yet understood. Yeah, this only happened, actually, starting with such work, it actually happened then afterwards. So this is two-body, yeah? Let's now divert a little bit and talk about three-body, yeah? As I said earlier, we are lucky that Bose-Einstein condensates are weakly interacting. They are certainly just super cool, yeah? And at those temperatures of a Bose-Einstein condensate, any metal is rock solid, yeah, evidently. So this only works because we have a dilute gas, and the process where three atoms meet and then start to cluster up is rather unlikely. Yeah? And it now could have been that we are all unlucky. We wouldn't be talking about this here now if these rates were just a factor of 10 or so rate coefficients. I'll come back to that in a second, what I mean by that. If they were just a factor of 10 or 20 or so worse, then we all would have a problem. Yeah. So what I'm talking about here is the process of three-body recombination, where three particles meet and they actually start populating. Two of them form a molecule with this binding energy, and all three partners in this comic here leave and take away a fraction of the binding energy, as indicated here. So this is a severe problem in principle, and it could have been disastrous. It turns out, no, it's not disastrous. And one can learn a lot about this. But one can then ask again the question later, what this process, how this process happens for molecules. Yeah? So we are talking about atoms here, the simple situation, and later we talk about molecules. Yeah. So in an atom trap, this leads to particle loss. With this, it leads to what we know as anti-evaporation, because it happens where the particles are densest and where the temperature is effectively the lowest, and that actually leads to usually it leads to heating, yeah, loss and heating, yeah, and it's not very much desired in a Bose-Einstein condensate, yeah. So now let's look at the situation where we add a third particle, yeah. Coming back to my situation here with the parabolic two-body bound state below threshold. On the right, scattering is positive. On the left, the scattering is negative. But what I've done now, I've added a third particle to this. Yeah. So what are the states associated with this situation? Yeah. As I indicated just a moment ago, what can happen is that upon a collision, you can populate the dimer state on the positive side, and even on the negative side, you could populate some lower lying dimer states. Yeah. And that can be not so useful, yeah. Apart from certainly having interesting physics, but for in the many-body context, we don't want that. So how do we quantify this? Well, we quantify this three-body scattering process in the simplest case without assuming any temperature changes and so on by the simple rate equation for the density with its rate equation coefficient L3. This L3 in this simple way gives us already a loss rate, approximate loss rate. Yeah. So the typical values for this L3 rate coefficient are these values that I'm giving here on the right, 10 to the 28, 10 to the minus 28 to 10 to the minus 30 cubic centimeters per second. We like cubic centimeters per second because we can immediately plug in our typical densities, BEC densities, 10 to the 13 atoms per cubic centimeters. And when you plug that in, you will see lifetimes, or 10 to the 14, then lifetimes are not infinite anymore, right? So they are finite, limited to that. So the first question after measuring this in the lab is, can one calculate L3? Yeah, and it turns out yes. And there's been a long endeavor on trying to do this at the various levels of sophistication. It turned out the first calculations were in the limit of a large positive scattering length. And this goes back to this work by Peter Fedichev and collaborators in the mid-90s, where this L3 coefficient was proposed to scale with the fourth power of the scattering length. And that already tells us, well, that's not too good, yeah, because increasing a scattering length from 100 Bohr radii like rubidium to 2000 like in cesium a factor of 20 increases this by a factor of 80,000, 20 to the 4th power. So that's a big number and increase. Okay, that's so an interesting scaling, and this was derived by basically dimensional analysis with proper prefactor h over m. And what actually at that time was not clear, what is the prefactor, constant prefactor, C here being in this case 3.9. What is this prefactor? I have to say a factor of 3 was taken out because when a collision happens, it was assumed that all 3 particles get lost, and so it makes sense to add a 3 here. So what is this factor C? And does it show some additional structure when you factor out a to the 4 scaling? And actually you can plug in a number for rubidium, and you get this number down here for this L3. So it reasonably agrees with what you measure in the lab. So after this work, various of our theory colleagues found out that this factor C is actually not really constant. For positive A, it actually oscillates with an upper limit that is actually 70. So not 4, but 3.9, but 70. And it turned out that calculating this L3 in the general case is non-trivial. And if you take this L3 for not a homonuclear situation where you have 2 species, rubidium and cesium, is actually something that is very complicated even nowadays. So I'm showing you some data from our lab long time ago, where we actually looked at this L3 coefficient. In fact, here we look at the 4th root because it's nicer to plot. And we call it row 3. We call it a row recombination length. And what we see on the positive side here, when you do 4th root here, you get essentially a linear scaling apart from small deviations that I can talk about later. But we see for negative scattering length, we see actually a drastic deviation from this A to the 4 scaling. So it tells us that this prefactor C of A that I introduced earlier, this one here, for negative A is actually strongly modulated. So what's happening here? And here are 2 data sets with a little hump for 200 nanokelvin, with a big hump for 10 nanokelvin. The red line is some simple theory that I will give a little later. So what's actually happening here? So, but just for the record, the 3-body loss rate goes through the roof. So by tuning your magnetic field from here to here, so here I'm plotting this as a function of the scattering length, but it turns out this is just a few Gauss, from here to here, about 10 Gauss. The 3-body loss coefficient for cesium goes from this value, increases by 6 orders of magnitude. So show me an example of a magnetic field effect where by tuning 10 Gauss, you get a change of 6 order of magnitudes. It's rare, certainly. I mean, you have to go through a phase transition to see that such an effect, I would claim. So what's happening here? And in fact, here also there's some modulations, that I will not go into details here now today, but I would just want to mention that, and I will give you a formula later. So there is some deviation from this linear scaling for the 4th root here. So what's actually happening? I'm going back to my 2-body situation here with this bound state. In fact, if you take 3 particles, it turns out there are novel states, 3-body bound states. They are actually known as Efimov states. And there's in fact an infinite series to ever weakening binding energy. So there's a ground state Efimov state, and then there are actually more with an interesting scaling. This product scaling. So a factor of 22.7, and I think we saw it already on the previous page. This 22.7 is actually basically a universal number. So but before I go into the details where this number comes from, is in fact what we were observing is this intersection point of this Efimov state hitting threshold here at this point at a specific value of the magnetic field or a specific value for the scattering length and causing this monstrous resonance. And in principle, there should also be a resonance here on the right where the Efimov states hits the dimer atom threshold. So where do they come from? Just very quickly. It's not the essence of my talk, certainly. Just for those who want to know, one can write down an effective radial equation for three particles interacting in the regime of where R is smaller than the scattering length and larger than the extent of the potential for the so-called hyperradius. And it turns out that in this one gets a 1 over R squared potential, and the bound states, very peculiar, and this 1 over R squared potentials are actually these Efimov states. And the scaling, they have this geometric scaling, and the scaling actually is because of e to the pi with S naught being almost unity, this factor up here. And that gives a binding energy change by a factor of more than 500 from one state to the other. And with this, one actually can already start counting how many Efimov states there are because of this exponential scaling, and details are found in this nice review here. So that gives rise to this modulation of C, yeah, and the fact that we have this un1 R squared potential that's actually well known from basic quantum mechanics, yeah, actually gives for the positive side this log cosine dependence of this A. So there is just let me walk you through this. It's very simple. You have a cosine dependence with a log dependence on the scattering length with some phase, yeah, I call it lambda star. And then some width parameter, how strongly this is actually modulated, this cosine, and I call it eta. Yeah, this is actually, turns out this is the recombination rate into the shallow dimer that I just discussed. And there's also a combination to loss into the deeply bound states, and that's actually that contribution. So that gives rise to modulation for positive A, and the maximum is here about 70 or so. But for negative A, this is actually 1 over that dependence here and shown here, yeah? So you have, again, a width parameter, but then you have this 1 over sine squared of log of A, and that gives rise to these drastic resonances in the 0 temperature limit. And that's actually, that's what we call these Efimov resonances, yeah. Okay, let me close this, yeah, but in the back, this is always in the background. When we have particles interacting with each other, Efimov physics and a drastic enhancement of the three-body loss rates to be kept in mind, yeah. So these Efimov states appear as resonant interactions for strong, for large scattering length. There's in principle an infinite series, and even higher order resonant Efimov states have been seen. Interestingly, they allow the Efimov states can basically be derived analytically. That's actually Efimov's realization. So the three-body problem has in mechanics an analytic solution. They come from this 1 over R squared potential, lead to this exponential scaling of states. Then that leads to this log periodic modulation of the loss rates for this as a function of the scattering length, and that's for positive and negative, and with pronounced resonance for negative A. And then actually one can even say more about this phase that I've not talked about, this phase, so of this of these oscillations. And in fact, that we think we sorted out some years ago, 10 years ago, but I don't go into details here. But it turns out that for certain potentials, one can make precise statements. What's a bit more complicated is how wide are these resonances, yeah, and that depends on the availability of bound states below, and there it's actually difficult to say something because that's depends on the specifics. And if you want to read some more, actually the second triatomic resonance was observed in Rudi Grimm's team some years ago. Okay, now let me see how time is doing. I think I have a few more minutes. So this closes this diversions. Now let me come to the dimers, back to the dimers, yeah. The
5 minutes.
5 minutes, yeah, I'm doing fine, yeah. And I see there is a chat question. Let me open this up.
a few questions. Shall I read it?
Okay, how the potential of F, let me read the second one first, become 1 over r squared? Well, you have to do this very, that's a good question. Yeah, I like it. Yeah, wonderful. You have to do this sort of, I call it Born-Oppenheimer type approximation when you treat the three-body problem. Yeah, you have to average out all the angular degrees of freedom and just then discuss the dependence on the hyperradius. And I think this is totally uncontrolled, this approximation. Efimov saw it, probably had enough intuition, but you have to do this. Born-Oppenheimer usually works because you have light electrons and heavy nuclei. Here we don't have nothing, there's nothing light here, yeah? But it still works to some extent. And then it turns out, and you have to do the math to get the 1 over r squared potential. And that's actually the big thing that Efimov did. So, okay, I could not fully answer that question, but it's actually a wonderful question, yeah? So can you comment on the spinor nature of alkali gases? Okay, so if yeah, this is a little bit off topic, yeah, we'll see whether this will be discussed further. When you have a spinor system, yeah, when you have, so that means basically you have the atoms being in different spin states coherently at the same time, coherently or non-coherently. You have usually slightly different scattering lengths, and in fact, for cesium, I think they're vastly different depending on the spin state. And I think with cesium, we have nothing done really spinor, but I have to be careful. Actually, we have done something, but I cannot, because of lack of time, talk about this. In general, this is a separate story, and I don't think I have the time to talk about this here. Yeah. Okay, so sorry for that. That would be something to talk about also with some of the experts who do this spinor or spinor physics with ultra-cold gases. Yeah, this has been done with rubidium, for example, with sodium, and I can, for example, highlight some very good work from Dan Stamperkern in Berkeley on spinor BTs. Okay, so let me turn to the dimer molecules. Yeah, if it allows me to turn. Okay, so why ultra-cold molecules? Let me back up one more time, yeah? Beyond what we said earlier, here are our favorite dimers, and certainly it's not just molecular BEC, dipolar quantum gases, perhaps some quantum simulation with that, yeah? Perhaps going in a regime where we can have long-range interactions in a layer where perhaps we can simulate high-temperature superconductivity. Well, I don't know. I have no idea whether this works. Nobody knows actually, yeah. But there's certainly other motivations that I should briefly mention, yeah. Ultra-cold chemistry, and we'll hear about this a bit later on. Fundamental physics, yeah. Preparing samples of molecules at low temperatures to be able to do spectroscopy with very high resolutions, yeah. For example, to search for an electron dipole moment or to look for time variation of the electron to proton mass ratio. And here, this iconic picture from Dave DeMille, quantum processing with dipoles that you switch on and off and that you let talk to each other. Admittedly, a bit more complicated than for ions in an ion trap, because ions in an ion trap, as you know, with a laser addressing, you can make every ion talk to every other ion in that chain. That's not so easy with dipolar molecules because they only talk to the neighbor. Okay, good. Okay, that's sort of a motivation, yeah. And let me talk about rubidium cesium here. It has a dipole moment of 1.27 dBi. And so you, to get a hold of that, you have to fully polarize the molecule by an electric field that's on the order of a few kilovolts. And we'll hear about this from Jun Yi tomorrow, how far you can polarize KRB until you run into problems. But I think they can do up to about 0.2 dBi or so, or 0.3. I forgot the exact number. Generally speaking, the dipole-dipole interaction is written down here in this Hamiltonian. Yeah, this is sort of the Hamiltonian without going to second quantization. Yeah, the very basic one. Yeah, it scales favorably with a inverse fine structure constant. So in contrast to the magnetic dipole. So that's why this is interesting. Admittedly, I've said this immediately. It's much easier to cool an atom, than a molecule, And so we'll see from Tilman, we see more about this. Okay, so where are as an outlook for tomorrow? Where are the interesting experiments on this? And various places. I've mentioned Junyi. We are working in rubidium cesium in Innsbruck, also on KCS and other places. And also I will briefly, if I have time, talk about our homonuclear endeavor, because that we learned a lot trying to control homonuclear cesium. Okay, so I think my time's up, So what we will be talking to, let me take slide as a motivation for tomorrow, So the plan is how to take an atom pair in the trap, in the lattice trap, to be more specific, with a distance of typically 50 microns, all the way to the ground state, where the size is 100 times smaller. So you have to reduce that internuclear distance, and at this point remove the binding energy of this molecule without heating the sample, So that's what we will be talking about partially tomorrow, and certainly the first the bottleneck that I already mentioned is creating that atom pair in the first place, here indicated just by 2 red dots, but it could be now any atom pair. Okay, I think Bora, you have to tell me. I think I'm it's up.
Yes, your time is up. There are a couple of questions. So, so first one is, if move states work for A tends to infinity, what about if A is small?
So it turns out, so the Efimov states appear in this resonant limit of A being very, very large, So if you had a zero range interaction potential, but with infinite binding energy, you can even have Efimov states all the way to negative binding energy. But it turns out Efimov states, there's a lowest lying Efimov states, and then you have only higher lying Efimov states. So it's cut off. And they typically appear around when the scattering length is on the order of a few times the van der Waals length, let's say 10 times. Then you expect the first Efimov state to pop up, and then as you increase A, you will get more and more of these Efimov states, but the scaling, certainly the binding energy scaling, is not very favorable. So you can actually look at the size of this Efimov state, So already the second or third Efimov state will already crash your trap, because they are too big.
Okay, and so then the next question is, can you find Efimov state in fermionic species?
Yes, there is Efimov states, so it's not in identical fermions, but with different spin states. In fact, there's been quite some work on seeing Efimov states with where the constituents are fermions. I should mention, the various groups. I don't want to say too much. For example, I think one group is at Georgia Tech, another group in Heidelberg. So there's been quite some work with fermionic atoms. And I see there's a question on, can you
think of radioactive elements such as radium as ultracold molecule?
I specifically haven't thought about radium, but a good candidate, for sure, a very interesting candidate, would be cesium 134, I believe. I always forget whether it's 142 or 34. It's a fermion, very heavy fermion, and it's not that bad. It can actually be made in a reactor, and it's not very badly radioactive. I think it's 134, and that would be nice. And I've briefly thought about that, whether we could do it. Well, our friends in Vienna, they have a reactor, and they could make it. But you would have to have your source, the source and your experiment next. I think it would be another fermion. As you all know, we don't have that many fermions in the field. Yeah, I mean, rubidium there's no fermion that it can be used. So there is lithium and potassium. They have fermionic isotopes, and then the elements like erbium or rhodium or strontium have fermionic isotopes. But so they're not. There's an abundance of bosons, but not that many fermions. With radium, certainly, I have no idea whether there's any chance of doing anything with this. Yeah, but we've certainly not carried that any further, and there are plenty of things to do with the present fermions, as we will see it during the school.
So is there any more question? So I'd also like to take the opportunity to give a big thank to Professor Hans-Christoph Nagerl for this wonderful educative talk. So
thank you very much. Yeah. I'm looking forward to tomorrow. Yeah. So are there efforts to trap the Efimov trimers? Yeah, good question. Well, the lifetime is rather short. Yeah. So the resonance width sets is essentially associated with a lifetime. So basically, these Efimov trimers are reaction channels, to be honest. Yeah. So in the case of, I mean, they will actually mediate the production of a lower lying dimer state and release a lot of binding energy. So that's basically a decay channel. So in our case, we are the lifetime would be rather short. It's less than a millisecond. I'm not saying that this is not possible, and we've never gone any further, I have to say. My plan is to pick this up a little bit, perhaps at some point. In particular, perhaps the next Efimov state is even a bit more stable, just by Frank Condon arguments, and perhaps then one has a chance to stabilize that. The group in Heidelberg by Selim Joachim, if I remember right, in fact, working with fermionic constituents, they actually even did some radio frequency spectroscopy on the binding energy some while ago. So it's, I don't know, 5-6 years ago or so. So there is something to do, yeah. And in fact, an interesting question is what happens with these Efimov systems when you really try to trap them and confine them, in particular in 2D or in 1D, and how this crossover from the 3D physics to 1D physics happens, and whether Efimov physics still exists in 1D. As far as I know, our theory friends tell us, strictly speaking, in 1D there are no Efimov states. But yeah, I would like to see the transition as you try to catch them in the lattice.
So, okay, so with that, I would like to give it back to the organizer. Thanks a lot, Christoph. Professor Nagerl will present again the lectures tomorrow at the same time. So thanks a lot for today, and I will give it back to the organizer.
Okay, I have to stop sharing my screen, I guess.
Thank you, thank you, Professor Nagerl. Yeah, so thanks for a nice talk. So we'll see you tomorrow again. And,
I see you tomorrow again, yes?
Yes, sure. Yeah, and we meet, so we'll take a break now for about 2 hours, and then we meet at 8 p.m. Indian time.
See you then, Christoph. Bye. Yeah, bye. Take care.
Good evening, Professor. Can you hear me? Professor, can you hear me? Can you please unmute your microphone?
Are you talking to me or to somebody else?
Okay, so sorry. So we are going to close this session.
Okay, fine, yeah.
Thank you.
Okay, see you later.
Yeah, Professor. See you.